Hello, friend. Some nights the sky holds secrets we've forgotten to ask about. There's a point of light up there, steady and rust-colored, that's been watching us longer than we've been watching it. Ancient Romans called it the god of war. We call it Mars. But what if it's neither a god nor a battlefield? What if it's a mirror showing us what a world looks like when it almost became home? Tonight we're drifting toward the red planet, not with rockets or math, just with wonder. And before we begin this quiet journey together, if you find peace in these slow explorations of the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, whispered softly, and ring the bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Mars sits approximately 140 million miles from Earth on average, though that distance breathes in and out as both planets orbit the Sun. Sometimes closer, sometimes farther, always there. It's roughly half the diameter of our world, and when you hold that thought, something shifts. Imagine Earth, then imagine it smaller, colder, lonelier. That's the neighbor we've been dreaming about for centuries. The ancient Egyptians called it Har-de-Cher, the red one. They tracked its movement across their night skies with careful precision, marking its retrograde loops as it appeared to move backward through the constellations. They didn't know about orbits or gravity. They just watched and wondered. That wondering, that patient observation spanning generations, was perhaps humanity's first love letter to Mars. We've been writing it ever since. In 1877, an Italian astronomer named Giovanni Schiaparelli looked through his telescope and saw what he described as canali on Mars, channels. The word was mistranslated into English as canals, and suddenly the world imagined not just water on Mars, but engineers, civilizations, beings who built vast networks to irrigate a dying world. Scientists now know these were optical illusions, tricks of light, and human hope meeting in the eyepiece. But that mistake reveals something tender about us. We wanted Mars to be alive so badly that we saw cities where there were only shadows. Percival Lowell, an American businessman turned astronomer, spent years mapping these imagined canals in exquisite detail. He built an entire observatory in Flagstaff, Arizona, dedicated to studying Mars. He drew intricate charts. He wrote books proclaiming that intelligent life must exist there, that the straight lines proved intentional design. He was wrong, of course, but his wrongness was beautiful in its way. He looked at a distant world and saw not just rocks, but possibility. He saw neighbors. The first real glimpse came in 1965, when Mariner 4 flew past Mars and sent back 22 grainy images. Scientists had expected forests, perhaps ice caps, maybe evidence of that ancient water everyone hoped for. What they got instead shocked them into silence. A dead world, cratered, cold, more like Earth's moon than Earth itself. One researcher reportedly went home and cried. The dream of a living Mars seemed to die that day in a room full of scientists staring at photographs of emptiness. But here's what's strange about grief. It makes you look harder. Those same researchers devastated by the barren landscape began to ask different questions. Not, where is the life? But, where did the life go? Because the craters themselves told a story. They revealed a planet with no significant atmosphere to burn up incoming asteroids. They showed a world exposed unprotected, and suddenly the question wasn't whether Mars had always been dead. It was when it died. Every 26 months, Earth and Mars reach opposition, the point where Mars, Earth, and the Sun form a straight line with Earth in the middle. During these moments, Mars appears brighter in our sky than at any other time. Ancient astrologers tracked these cycles meticulously. They noticed patterns, rhythms. Mars would blaze bright, then dim, then vanish in the sun's glare, then return. To them, it was a celestial drama. To us, it's orbital mechanics. But the feeling, that sense of a distant world reaching toward us periodically, that feeling remains the same across millennia. When you look at Mars through even a small telescope today, You can see the polar ice caps. They gleam white against the rust. They grow and shrink with the Martian seasons, which last about twice as long as ours because Mars takes 687 Earth days to orbit the Sun. Watching those ice caps expand and contract, you're witnessing weather on another world. You're seeing winter arrive somewhere 140 million miles away. It's strangely intimate, that observation, like watching someone's breath fog a window from across a vast dark room. The color itself deserves a moment. That famous red comes from iron oxide rust, coating the surface in a fine dust that gets lifted into the atmosphere during storms. Mars is a planet oxidizing, slowly rusting in the thin air. It's a world caught in a chemical process that on Earth would suggest moisture life, organic decay. On Mars, it suggests the opposite, a world so dry that even its iron bleeds color into the sky. The sunsets there aren't blue like ours. They're blue-gray tinged with warmth. The dust scatters light differently. Standing on Mars, you'd watch the sun set and see your home planet's colors inverted. Red sky at morning on Earth, blue sky at evening on Mars. There's a peculiar loneliness to Mars that scientists struggle to put into words. It's not just that it's far, the outer planets are far. It's that Mars is almost right. It has a 24-hour and 40-minute day so close to Earth's that our circadian rhythms would barely notice. It has seasons, ice clouds, even snow that falls from the Martian sky, though it's carbon dioxide snow, not water. It has mountains taller than Everest and canyons that would swallow the Grand Canyon whole. It has weather, geology, chemistry. It has almost everything Earth has, except it's quiet. Profoundly, absolutely quiet. No wind that howls, no oceans that crash. Just a whisper of atmosphere that's 1% the thickness of Earth's and dust that drifts rather than storms most of the time. Do you ever wonder what it would feel like to stand there? Not the mechanics of it, not the suit or the radiation or the cold, just the feeling. To be the only warm thing on an entire world. To look up and see Earth as a blue star, no bigger than Venus, appears to us. To know that everything that ever loved you, every voice that ever spoke your name, every tree you ever climbed, exists on that tiny point of light impossibly far away. That's the emotional gravity of Mars, not its physical pull that's only 38% of Earth's, but its existential weight. In the late 1800s, H.G. Wells wrote, "The War of the Worlds," imagining Martians invading Earth not out of malice but desperation. Their world was dying, he wrote, and they looked at Earth with envious eyes. That image stuck. It embedded itself in human consciousness so deeply that when Orson Welles broadcast a radio adaptation in 1938, thousands of Americans believed Mars had actually invaded. They fled their homes. They called police stations. They prepared for the end. All because Mars had become, in our collective imagination, the place where the almost human lived, where things like us, but not us, looked back with hunger. We know now there are no Martians with tripods and heat rays. But Wells wasn't entirely wrong. Mars is desperate in its way. It's a world that once had what Earth has. Researchers now believe that 4 billion years ago, Mars had rivers, lakes, possibly an ocean covering its northern hemisphere. It had a thicker atmosphere, warmer temperatures, a protective magnetic field. It had the ingredients. And then something happened. The magnetic field collapsed. The solar wind stripped away the atmosphere. The water evaporated or froze beneath the surface. Mars didn't die violently. It died slowly over 1 billion years, losing its breath one molecule at a time. That's the dream we're chasing when we send rovers to Mars. Not the dream of finding little green men, but the dream of finding proof that a planet can live, can hold oceans and clouds and maybe even algae or microbes, and then can lose it all. Because if Mars once lived and died, then life isn't just possible elsewhere, it's also fragile everywhere. Even here, even home. The dream of Mars has always been a dream about time, about looking at a world and seeing not what it is, but what it was and what it might become again. Every mission we send there is a question posed across space. Are we alone? were we ever? And perhaps more urgently, could Earth become Mars? Could we wake up one day, a billion years from now, as a cold red desert where oceans used to sing? Tonight, as you drift towards sleep, Mars is out there moving through space at 54,000 miles per hour. You're moving to on Earth at 67,000 miles per hour. Two worlds hurtling through the dark, orbiting the same star, sharing the same sunlight, separated by an ocean of nothing. And yet, we've touched it. We've sent pieces of ourselves there. We've left footprints in a way, not human footprints, not yet, but the tracks of rovers that carry our curiosity across its dust. The Red Dream isn't about conquest. It never was, really. It's about recognition. It's about looking at a world that almost became like ours and asking, what happened to you? And listening in the silence for an answer that might also be a warning or a promise or both. The story of Mars is still being written. And the next chapter begins not with what Mars is now, but with what it once was. 4 billion years ago, when water flowed freely and the sky was thick enough to hold warmth, Mars was different. It was younger. It was alive, perhaps. And that ancient face of Mars, that world of rivers and rain, is where we'll drift next. Imagine a world where rain fell softly on red soil, where rivers carved their way through valleys that had never known silence, where an ocean dark and vast lapped against shores that would one day turn to dust. That world existed. It wasn't Earth. It was Mars 4 billion years ago, wearing a face we would barely recognize today. The evidence sits in the rocks, patient and quiet, waiting for us to read it. In 2012, the Curiosity rover rolled into Gale Crater and found something that made geologists lean closer to their screens. Rounded pebbles, smooth stones embedded in the ancient sediment. On Earth, you find stones like that in riverbeds tumbled by water over years, decades, centuries. The edges wear down, the shapes soften. Water does that. Only water does that. And here they were, sitting on Mars Jung-Ren to a river that flowed 3.7 billion years ago, carrying rocks downstream under a sky we can only imagine. The crater itself tells a longer story. Gale Crater is 96 miles wide, created by an asteroid impact roughly 3.5 to 3.8 billion years ago. But what interests scientists isn't the crater, it's what filled it afterward. Layer upon layer of sediment stacked like pages in a book, each one recording a different chapter of Martian climate. At the center rises Mount Sharp, a mountain 3.4 miles high made entirely of these layered deposits. It shouldn't exist not like this. On Earth, craters fill with sediment and stay flat. But Mount Sharp grew upward layer after layer, possibly formed by wind after the water left, or perhaps by the slow accumulation of material in an ancient lake that once filled this crater to its rim. Either way, it's a monument to deep time, to a Mars that had weather complex enough to build mountains from settled dust. Curiosity drilled into a rock called John Klein in 2013, extracting powder from 2.5 inches deep. The analysis revealed clay minerals, specifically smectite clays, which form only in the presence of water, with a neutral pH, not too acidic, not too alkaline. The kind of water you could theoretically drink, the kind of water that wouldn't immediately destroy organic molecules. Scientists describe this as a habitable environment, though they choose their words carefully. Habitable doesn't mean inhabited. It means conditions were right. It means the door was open, even if no one walked through. But let's go back further. Before Gale Crater existed, before the impacts that scarred Mars into the cratered landscape, we recognize there's evidence of something extraordinary. The northern hemisphere of Mars sits noticeably lower than the southern hemisphere, a difference of about 3 miles in elevation. This dichotomy has puzzled scientists for decades. One hypothesis suggests that the northern lowlands once held an ocean, possibly covering a third of the planet's surface. They even have a name for it, Oceanus Borealis, the Northern Ocean. Researchers have mapped what might have been ancient shorelines, tracking elevation contours that run parallel like ghostly tide marks frozen in time. Some of these proposed shorelines match up almost too perfectly with where an ocean would have settled, given Mars's rotation and gravity. Others are more ambiguous, scattered, or disrupted by later geological activity. The debate continues polite and intense, but the possibility remains Mars may have once been a water world. The Mars Reconnaissance Orbiter has identified valley networks across the Martian surface, branching patterns that look startlingly similar to river systems on Earth, viewed from space. These aren't just straight channels cut by lava or ice. They branch, they merge, they follow topography, the way water does when it flows downhill, seeking the path of least resistance. The largest of these Rule Valley stretches over 900 miles, roughly the distance from New York to Chicago. Imagine that. A river system longer than the Mississippi's main channel, flowing under a sky that might have been thick enough to hold clouds, maybe even rain. Rain on Mars. The phrase sounds like poetry, but scientists now believe it happened. Not the gentle drizzle we know on Earth, but something stranger. With Mars's lower gravity, 38% of Earth's raindrops would have fallen differently. They would have been larger, slower, drifting down through an atmosphere that was thicker than today's wisp, but still thinner than Earth's blanket. Computer models suggest these ancient Martian raindrops could have been twice the size of Earth's falling at half the speed, creating a precipitation that would have felt softer, dreamier, less like rain, and more like a slow descent of possibility. The atmosphere itself is the key to this ancient Mars. Today, Mars's atmosphere is 95% carbon dioxide, but so thin that standing on the surface you'd experience less than 1% of Earth's atmospheric pressure. It's essentially a vacuum. But isotopic analysis of gases trapped in Martian meteorites, rocks blasted from Mars by impacts and eventually falling to Earth, reveals that Mars once had much more atmosphere. The lighter isotopes of gases like argon and carbon dioxide are missing, likely stripped away into space over billions of years. What remains is heavier, denser, the isotopic signature of a planet that lost most of its air to the solar wind. By measuring these ratios, scientists estimate Mars's ancient atmosphere could have been 20 to 40 times thicker than it is now. Still less dense than Earth's, but enough. Enough for liquid water, enough for weather, enough perhaps for life. Here's where the story grows more complex. That ancient atmosphere needed protection, and Mars had a global magnetic field. The Mars Global Surveyor discovered in the late 1990s that regions of Mars's crust, particularly in the southern highlands, retain remnants of powerful magnetization. These magnetic anomalies are frozen in ancient rock, fossilized magnetic fields locked in place when the rocks cooled billions of years ago. Earth's magnetic field is generated by its liquid iron core, churning and spinning, creating a protective bubble called the magnetosphere that deflects the solar wind, the stream of charged particles constantly flowing from the sun. Mars once had this protection too. But sometime around 4 billion years ago, Mars's core cooled enough that the dynamo died. The magnetic field collapsed. And without that shield, the solar wind began stripping away the atmosphere molecule by molecule over millions of years. This wasn't a sudden death. It was erosion, atmospheric erosion. NASA's MAVEN mission, launched in 2013 specifically to study this process, watches it happening in real time, even now. MAVEN measures the rate at which Mars currently loses atmosphere to space, about 100 grams per second. That sounds like nothing 3.5 ounces every second, but multiply that by 1 billion years. Over deep time, it's catastrophic. The solar wind doesn't blow uniformly either. During solar storms, when the sun erupts with coronal mass ejections, MAVEN has measured atmospheric loss rates increasing by a factor of 10 or more. Mars becomes more vulnerable during these storms, gasping, losing its breath faster. There's a haunting timeline here. Mars had water, Mars had an atmosphere, Mars had a magnetic field. And then the field died, and the atmosphere thinned, and the water, where did the water go? Some of it evaporated into space, broken apart by ultraviolet radiation into hydrogen and oxygen, the hydrogen escaping Mars's gravity entirely, while the oxygen bonded with iron in the soil, rusting the planet into the red world we see today. But some of the water stayed. It went underground, freezing into vast reservoirs of subsurface ice. The Phoenix lander in 2008 dug into Martian soil and found water ice just inches below the surface. Radar instruments on orbiting spacecraft have detected massive sheets of ice buried beneath the plains, ice deposits meters thick extending for miles. Mars didn't lose all its water. It buried it like a memory too cold to revisit. The Perseverance rover currently exploring Jezero Crater chose that location for a specific reason. Jezero, like Gale, was once a lake, but Jezero had something more, a river delta. Orbital images clearly show the fan-shaped deposit where a river once emptied into the crater lake, carrying sediment that settled layer by layer over who knows how many years, tens of thousands, millions perhaps. River deltas on Earth are rich with life-teeming ecosystems where water meets land meets nutrients. There are places where organic molecules accumulate, where microbes thrive, where fossils form. If life ever existed on Mars, a place like Jezero would be where you'd most expect to find evidence of it. Perseverance is currently collecting rock samples from this ancient delta, sealing them in titanium tubes to be retrieved by a future mission, and brought back to Earth for analysis in laboratories far more sophisticated than anything we can fit on a rover. But here's the weight of it. All this water, all this weather, all these rivers and lakes and possible oceans existed on Mars at the same time that life was beginning on Earth. 4 billion years ago, Earth was a young world still being battered by asteroids, its surface molten in places, its oceans just forming. And yet, somehow, life emerged here. We don't know exactly when or how, but the earliest evidence of life on Earth dates to around 3.8 billion years ago. Stromatolites, layered structures built by microbial mats. That's almost exactly the same era when Mars had liquid water on its surface. 2 planets orbiting the same star, both with water, both with chemistry. Earth rolled the dice and got life. Mars rolled the dice and got what we don't know yet. That's the question that drives every mission, every rover, every carefully chosen landing site. There's a concept in planetary science called the window of habitability. It's the period during which a planet has conditions suitable for life, liquid water, organic chemistry, energy sources. Earth's window has stayed open for billions of years. Mars's window, it seems, closed relatively quickly. Maybe 500 million years, maybe less. A geological blink. If life emerged on Mars, it had to happen fast during that narrow window, before the atmosphere thinned too much, before the water froze or evaporated, before the planet's warmth bled away into space. That urgency, that narrowness, makes the search for Martian life feel more poignant. It's not just about whether life exists elsewhere. It's about whether life can begin and then be erased, its story interrupted before it could write itself fully. Did ancient Martians, if they existed at all, witness their world dying? Of course not. Nothing intelligent enough to witness existed probably. If there was life, it was microbial. Simple living in the water or the soil, unaware of atmospheres or magnetic fields. But those microbes, if they were there, experienced the change nonetheless. Slowly, over millions of generations, the ponds would have dried up. The rivers would have stopped flowing, the ice would have crept in, and life, if it was, there would have retreated to wherever water remained, underground, springs, subsurface ice, deep aquifers, or it would have gone extinct, leaving behind only the faintest chemical whispers in rocks we're only now learning to read. This is what makes Mars both hopeful and heartbreaking. It's a planet that had its chance. It was given the ingredients water warmth time, and then they were taken away not by any catastrophe, not by violence, but by physics. By the size of the planet too small to hold its core heat forever. By the distance from the sun just a bit too far. By the absence of a large moon to stabilize its rotation. By chance, in other words. Mars lost the cosmic lottery not because it did anything wrong, but because it was born slightly too small, orbiting slightly too far out in a solar system where luck matters as much as chemistry. And yet, even in its death, Mars teaches us something about resilience, because the water didn't vanish completely. It's still there, frozen, waiting. The minerals formed in that ancient water are still there, locked in rock. The story is still there, written in sediment layers and valley networks and magnetic ghosts in the crust. Mars is a planet that remembers. It may be a cold memory, a fossil memory, but it's memory nonetheless. And we're learning to read it slowly, carefully, with robots that move at the speed of caution across terrain that hasn't heard footsteps in 4 billion years, if it ever heard them at all. When we look at Mars now, we're seeing its old age. But beneath that age, buried under dust and time and silence, there's a younger Mars, a Mars of rivers and rain, a Mars that almost became another Earth. That ancient face, that wet world is what we're searching for in the rocks. And in those rocks, there might be something even more profound than water. There might be traces of life itself, fossils so small we'd need microscopes to see them, chemical signatures that say, yes, something lived here, something breathed or ate or divided, or simply existed for a moment in the long story of this planet. That possibility draws us forward into the search, into the patient work of looking for ancient life in red dust. And that's where our journey goes next, into the question that every Mars mission ultimately asks, did anything ever call this place home? What does a fossil look like when it's 4 billion years old and smaller than a human hair? How do you prove that something lived when all that remains is a whisper of chemistry and stone? These aren't philosophical questions. They're the actual challenge facing scientists who search for ancient life on Mars. Because if microbes ever existed there, they left behind evidence so subtle, so easily mistaken, that finding it requires us to question everything we think we know about what life looks like when it's gone. On August 7th, 1996, NASA held a press conference that made headlines around the world. They presented a meteorite, a rock designated ALH 4001, found in Antarctica in 1984. This rock, they explained, had been blasted off Mars by an asteroid impact roughly 17 million years ago, drifted through space, and eventually fell to Earth about 13,000 years ago. Inside this meteorite, researchers had found something extraordinary, tiny structures that looked like fossilized bacteria, organic molecules called polycyclic aromatic hydrocarbons, and microscopic crystals of magnetite, arranged in chains similar to those produced by certain Earth bacteria. President Clinton gave a speech. The world wondered, had we found proof of life on Mars? The answer, it turned out, was more complicated than anyone wanted it to be. The structures in ALH 84001 were real. Under electron microscopes, they appeared tubular segmented, roughly 20 to 100 nanometers long. That's extraordinarily small, about 1/100th the width of a typical Earth bacterium. Too small, some scientists argued, to contain the molecular machinery needed for life, as we understand it. Others countered that maybe Martian life was different, more compact, or that what we were seeing were the outer shells of cells whose interiors had long since degraded. The debate became technical, intense, and ultimately unresolved. Some researchers still believe ALH 84001 contains evidence of ancient Martian life. Others are convinced the structures formed through non-biological chemical processes. And that ambiguity, that inability to say definitively yes or no, reveals the central challenge: life's fingerprints and chemistry's accidents can look startlingly similar. This is what scientists call the problem of biosignatures, signatures of life. On Earth, we know what to look for. Fossils have certain shapes, certain mineral compositions. Organic molecules arrange themselves in patterns that biological processes favor. Isotopes of carbon show preferential ratios. because living things like lighter carbon 12 over heavier carbon 13 when building their cells. But all of these signatures can also be produced by non-biological processes under the right conditions. Hot springs can create organic molecules. Crystals can grow in shapes that mimic cells. Isotope ratios can shift through geological reactions that have nothing to do with life. The universe, it turns out, is very good at creating false positives, at making us see life where there might be only chemistry playing tricks. Curiosity rover drilled into Martian mudstone in 2014 and detected organic molecules, specifically chlorobenzene and dichloroalkanes. These are complex carbon compounds, and their presence excited researchers. But here's the complication. Curiosity's sample analysis system heats Martian soil to extremely high temperatures to release volatiles for measurement. That heating process, combined with perchlorate salts naturally present in Martian soil, can create organic molecules from non-organic carbon. So, were these molecules evidence of ancient life, or were they created in the oven of the rover's own instrumentation? Scientists had to carefully compare the types and amounts of organics detected, running simulations and controls, ultimately concluding that, while some organics were likely instrument artifacts, others seemed genuinely Martian in origin. But Martian doesn't mean biological. It just means they were there in the rock before curiosity heated them up. Where they came from, life meteorites, geological chemistry remains unknown. The Perseverance rover carries an instrument called SHERLOC, which stands for Scanning Habitable Environments, with Raman and luminescence for organics and chemicals. It's essentially a sophisticated flashlight that can identify organic compounds and minerals without destroying the sample. In 2022, SHERLOC detected organic molecules in multiple rock samples from Jezero Crater. The molecules showed up in association with minerals formed in water, which is promising. But again, the question lingers: biological or not? Organics from life, or organics from the steady rain of carbon-rich meteorites that have been falling on Mars for billions of years? The answer requires more analysis than a rover can perform. It requires bringing samples back to Earth, studying them with every analytical tool we have, comparing them against every known non-biological process. That's why sample return missions matter so much. The rock has to come home for the question to be answered. Let's talk about stromatolites for a moment, because they represent Earth's oldest clear evidence of life. Stromatolites are layered structures built by microbial mats, communities of bacteria that trap sediment and precipitate minerals, growing slowly over years into dome-shaped formations. The oldest confirmed stromatolites on Earth date back 3.5 billion years, found in Western Australia. They're not fossils of individual organisms, but rather fossils of biological architecture, proof that microbes were collectively shaping their environment. Scientists have looked for similar structures on Mars. Certain layered rock formations photographed by rovers superficially resemble stromatolites. But the resemblance isn't enough. Geological processes can create layers too. Sediment settling in still water, chemical precipitation, volcanic ash deposits. Without being able to examine the microscopic structure, without finding the biological textures that distinguish stromatolites from regular sedimentary layers, we can't conclude anything. We can only wonder and keep looking. Here's a truth that's hard to accept. Even if ancient Martian life existed, we might never find definitive proof. Fossilization is rare. Most organisms that die don't fossilize, they decay, scatter, rejoin the chemical cycles of their environment. On Earth, with 4 billion years of continuous life and active geology that constantly recycles rock, we have gaps in the fossil record spanning millions of years. Mars has been geologically quieter for billions of years, but it's also been subjected to intense radiation, temperature swings, and oxidizing chemistry that breaks down organic molecules. Any fossils that once existed might be so degraded, so altered, that they're unrecognizable. Or they might still be there pristine and waiting buried under meters of dust in a location we simply haven't reached yet. The absence of evidence isn't evidence of absence. It's just silence, and silence is hard to interpret. Methane adds another layer to this mystery. Mars has methane in its atmosphere, but in tiny variable amounts measured in parts per billion. The Curiosity rover has detected seasonal methane spikes in Gale crater concentrations that rise and fall over the Martian year. The European Space Agency's Trace Gas Orbiter has also detected methane, though its measurements don't always align with Curiosity's, which has sparked healthy scientific debate about measurement techniques and atmospheric dynamics. Why does methane matter? Because on Earth, most atmospheric methane is produced by life, specifically by microbes called methanogens, that live in oxygen-free environments like swamps and the guts of animals. But methane can also be produced geologically through reactions between water and certain minerals deep underground, a process called serpentinization. Mars could have active serpentinization happening right now in subsurface aquifers where water contacts olivine-rich rock. Or it could have methanogenic microbes living deep underground, producing methane that seeps up through cracks and vents into the atmosphere. Both explanations fit the data. Neither can be proven without going deeper literally and figuratively into Mars. There's a particular kind of frustration in this search, a feeling that we're always one measurement away from certainty. Scientists call it tantalizing ambiguity, data that hints and suggests, but never quite confirms. The Viking landers in 1976 conducted 3 experiments specifically designed to detect life. One experiment, the labeled release experiment, returned results that even today look biological. When Martian soil was mixed with nutrients and water, it released radioactive carbon dioxide in a pattern consistent with metabolism. But a separate experiment that heated soil to detect organic molecules found nothing. How could there be metabolism without organic molecules? The lead scientist Gilbert Levin believed until his death in 2021 that Viking had detected life. NASA's official stance is that the results were likely produced by reactive chemistry in the soil, not biology. Both interpretations rely on the same data. The ambiguity remains. Think about what this means for a moment. We sent 2 spacecraft to Mars almost 50 years ago, and we still can't agree on whether they found life. That's not a failure of science, it's a testament to how difficult this question actually is. Life is a process, not just a substance. It's chemistry that self-organizes, that reproduces, that evolves. But when life dies and becomes a fossil, the process stops. All that remains are the chemical byproducts, the structural residues, the isotopic preferences. And without a living example to compare against, without knowing what Martian biochemistry might have looked like, we're trying to recognize a signature we've never actually seen. Perseverance is currently caching samples specifically chosen for their potential to preserve biosignatures. One sample, nicknamed Berea, comes from a rock rich in carbonate minerals, the same type of rock that preserves fossils well on Earth. Another sample contains fine-grained sediments deposited in still water, the kind of environment where delicate biological structures might settle and be entombed before decay. These samples are sealed in ultra-clean titanium tubes, each one a time capsule holding perhaps the most important question humanity has ever asked about another world. The plan is for a future mission to retrieve these tubes and bring them back to Earth, possibly by the early 2030s. Until then, they sit on Mars, waiting, holding their secrets in sterile darkness. But here's what keeps scientists awake at night. What if we bring back Martian samples and find something that looks biological, smells biological, seems biological, but we still can't prove it? What if the ambiguity follows us home? There are protocols in place. The samples will be studied in maximum containment facilities, the same kind used for dangerous pathogens, not because anyone seriously thinks Martian microbes could threaten Earth, but because we need to keep Earth's biology from contaminating the samples. The contamination works both ways. A single Earth bacterium that hitches a ride could multiply in the lab and create signals we'd mistake for Martian life. The whole endeavor requires obsessive sterility, patience, and a willingness to accept that even with Mars rocks sitting in our laboratories, we might still be left with probabilities rather than proof. There's a concept called the ladder of life detection, a framework developed by astrobiologists to evaluate potential biosignatures. It has rungs, each one representing increasing confidence. Finding organic molecules is the bottom rung, interesting, but not conclusive. Finding organized structures that look cellular is a higher rung. Finding isotopic patterns consistent with metabolism is higher still. Finding multiple independent lines of evidence that all point toward biology, finding structures and chemistry and patterns that together become impossible to explain any other way. That's the top rung. That's proof. We haven't reached it yet for Mars. We're somewhere on the middle rungs, climbing carefully aware that one wrong step, one misinterpreted measurement could send us back down. Do you ever wonder if ancient Martians, if they existed, left anything behind intentionally? Of course not. Microbes don't build monuments, but they do leave chemical calling cards, patterns in the rock that say, something consumed this, something excreted that, something preferred this molecule over that one. Those patterns are the monuments, subtle and quiet, waiting for observers patient enough to read them. And we're learning that patience slowly through rovers that move inches per day, through instruments that take hours to analyze a single grain of dust, through scientists who spend careers interpreting data that never quite says yes, but also refuses to say no. The search for ancient life on Mars is fundamentally a search for kinship, for evidence that life isn't a miracle that happened once on one world, but a possibility that emerges wherever conditions allow. If we find fossils, even microbial fossils, it changes everything. It means the universe is less lonely than we thought. It means chemistry becomes biology, not through divine accident, but through something more reproducible, more common. It means we're not orphans in the cosmos, but rather one example among potentially billions of worlds where matter organized itself into something that could be called alive. And if we don't find fossils, if Mars turns out to have been always barren despite its water and warmth, that's profound too. It means life is rarer, more precious, more dependent on factors we don't yet understand. Either answer yes, there was life, or no. There wasn't reshapes how we see ourselves in our place. That's why we keep searching, keep drilling, keep hoping that somewhere in the red dust, there's a truth waiting to be careful held. But life, if it existed on Mars, wouldn't have lived in isolation from its environment. It would have adapted, evolved, found ways to survive in conditions that seem impossible. And that's exactly what we see on Earth, in places that mirror Mars in their harshness. There are organisms on our planet that thrive where nothing should survive, and they show us the blueprint for what Martian life might have been like. Those extremophiles, those survivors, offer us hope written in DNA. And it's to them, to Earth's toughest citizens, and what they reveal about life's possibilities that we turn our attention now. There's a creature so small, you'd need a microscope to see it, so resilient it can survive the vacuum of space, and so stubborn it refuses to die, even when frozen, boiled, irradiated, or deprived of water for decades. It's called a tardigrade, and it's rewriting everything we thought we knew about what life needs to survive. If we want to understand what might live on Mars, we don't need to imagine alien biology. We just need to look at Earth's extremophiles, the organisms that thrive where nothing should survive. They're not science fiction, they're science fact, and they're showing us that life's boundaries are far wider than we ever dreamed. The tardigrade, affectionately called the water bear, because of its lumbering bear-like walk under magnification, measures about 0.5 millimeter long. It has 8 legs, a segmented body, and a face that looks perpetually surprised. But its appearance isn't what makes it remarkable. What makes it remarkable is what happens when conditions turn harsh. When a tardigrade faces desiccation complete, drying out, it contracts into a structure called a ton, expelling nearly all the water from its cells and replacing it with a sugar called trehalose that forms a glass-like protective matrix around its proteins and DNA. In this state called cryptobiosis, the tardigrade isn't quite alive and isn't quite dead. It's paused. Its metabolism drops to 0.01% of normal. It can remain in this state for years, possibly decades. When water returns, the tardigrade rehydrates, and within hours it's walking around again, as if nothing happened. Researchers have revived tardigrades after 30 years of frozen storage. Some studies suggest they could survive even longer. In 2007, the European Space Agency sent tardigrades into low Earth orbit aboard the Photon M3 spacecraft. For 10 days, the tardigrades were exposed to the vacuum of space cosmic radiation and solar UV radiation at levels that would kill most Earth organisms within minutes. When they returned, researchers rehydrated them. Many survived. Some even reproduced afterward, producing healthy offspring. This wasn't a fluke. Subsequent experiments have confirmed it. Tardigrades can survive space not because they evolved for space, but because the extreme adaptations they developed for surviving temporary droughts on Earth happened to work in an environment far harsher than anything our planet offers. It's accidental resilience, but it's real. And it tells us something profound. Life doesn't need Earth-like conditions to persist. It just needs enough water occasionally to wake up. Now, think about Mars. We know Mars has water frozen in the soil and possibly liquid in deep aquifers. If a tardigrade-like organism ever evolved on ancient Mars, could it still be there today, dormant in the regolith, waiting for the rare moment when subsurface ice melts during a geothermal event or a meteor impact? It sounds like fantasy, but the biology says it's possible. Dormancy is a proven survival strategy. The question isn't whether life could theoretically wait, it's whether life was ever there to wait in the first place. Let's travel to the Atacama Desert in Chile, one of Earth's driest places. Some regions of the Atacama receive less than 1 millimeter of rainfall per year. Parts of it haven't seen rain in recorded history. NASA uses the Atacama as a Mars analog site because the soil chemistry, the aridity, and even the UV radiation levels approximate Martian conditions more closely than almost anywhere else on Earth. And yet, life exists there. Microbes live in the Atacama soil in a state of near-suspended animation, their metabolisms barely ticking over. When researchers analyzed Atacama soil, they initially thought it was sterile. No culturable bacteria grew on standard laboratory media. But when they used molecular techniques to directly sequence DNA from the soil, they found microbial communities dormant but alive, waiting for the rare rain that comes once or twice a decade. When rain does fall, these microbes explode into activity, reproducing rapidly, consuming nutrients, then returning to dormancy before the moisture evaporates. They live on the edge of death, but they live. In 2017, an unusually heavy rain fell in the Atacama, the kind of event that happens once in several decades. Scientists rushed to the desert to see what would happen. Within hours, the dormant microbial communities awakened. Within days, they had reproduced and the microbial population density increased by orders of magnitude. Within weeks, as the moisture disappeared, they returned to dormancy. The entire bloom and bust cycle happened faster than a single season, a microbial explosion compressed into the brief window when water existed. If Mars has similar events, perhaps subsurface ice melting temporarily due to geothermal heat or seasonal temperature shifts, could Martian microbes, if they exist, be doing the same thing, blooming in the dark, deep underground, in cycles no rover has witnessed? Because they happen in places we can't see. The McMurdo Dry Valleys in Antarctica represent another Mars analog, perhaps the closest we have. These valleys receive less than 10 centimeters of snow per year, which usually sublimates turns directly from ice to vapor before it can melt. The soil is frozen, the air is dry. and the landscape looks more like Mars than like the Earth most people know. In 1978, scientists discovered Don Juan Pond in one of these valleys, a body of water so salty it doesn't freeze even at temperatures far below 0 Celsius. The salinity is over 40%, nearly 12 times saltier than seawater. And yet, in samples from this brine, researchers have found microbial life halophiles, salt-loving organisms that have adapted to concentrations of salt that would desiccate and kill most cells. These organisms use specialized proteins and accumulate organic solutes inside their cells to balance the osmotic pressure, preventing water from being sucked out of their cytoplasm. It's biochemical engineering honed over millions of years of evolution in extreme environments. Here's why this matters for Mars. The water we've detected on Mars, particularly the recurring slope lineae, those seasonal dark streaks that appear on slopes during warmer months, is likely briny saturated with salts called perchlorates. Pure water can't exist as a liquid on Mars's surface because the atmospheric pressure is too low. It would immediately boil away even at freezing temperatures. But salty water has a lower freezing point and a lower boiling point, creating a narrow temperature range where liquid brine can exist. If Earth's halophiles can thrive in Don Juan Pond's extreme brine, could similar organisms survive in Martian perchlorate brines? The chemistry is different. Perchlorates are more reactive and generally considered toxic, but life has surprised us before. Some Earth bacteria actually use perchlorate as an energy source, breaking it down to access oxygen. What's poison to one organism is food to another. Toxicity, it turns out, is context-dependent. Deep beneath Earth's surface, far from sunlight, there exists an entire biosphere we barely knew about until recently. These are endolithic microbes, organisms that live inside rock. In the 1990s, scientists drilled into basalt formations in the Columbia River Basin and discovered bacteria living more than a kilometer underground in cracks and pores within the rock itself. These microbes don't photosynthesize. They can't because no light reaches them. Instead, they derive energy from chemical reactions between minerals and water, a process called chemosynthesis. They eat rock, essentially breaking down iron-rich minerals to extract electrons using hydrogen and methane, seeping up from deeper in the crust. They live slowly. Some of these microbes are estimated to divide only once every 100 years or more. But they live, and they've been doing so, for potentially millions of years, isolated from the surface world, unaware that sunlight even exists. Mars has basalt. It has subsurface water frozen now, but possibly liquid in deeper, warmer regions. It has minerals that could support chemosynthesis. If endolithic life exists on Mars, it would be living kilometers below the surface, beyond the reach of rovers, beyond the destructive effects of surface radiation, in a stable environment where temperature and pressure have remained relatively constant for billions of years. We wouldn't find it by driving rovers across the surface. We'd have to drill, and drilling on Mars with current technology is extraordinarily difficult. Perseverance's drill can penetrate a few centimeters. To reach potential endolithic biospheres, we'd need to drill hundreds of meters at minimum, possibly kilometers. It's a technical challenge we haven't solved yet, but the biological precedent from Earth tells us it's worth trying. There's a place in Romania called Mobile Cave, sealed off from the surface for 5.5 million years. The cave's ecosystem runs on chemosynthesis, fueled by hydrogen sulfide gas seeping from deep rocks. No sunlight has entered this cave for millions of years, yet it contains a full ecosystem, bacteria, fungi, and even larger organisms like spiders, scorpions, and isopods, all descended from ancestors that adapted to the cave's chemistry when it was sealed. The bacteria form floating mats on the cave's lakes, metabolizing sulfur and producing organic compounds that feed the entire food web. It's a complete biosphere that operates on entirely different energy economics than the surface world. If a sealed cave on Earth can sustain life for millions of years without sunlight, Why couldn't subsurface pockets on Mars do the same fed by geothermal heat and chemical energy from rock-water interactions? Psychrophiles, cold-loving organisms, thrive in Earth's polar regions at temperatures well below freezing. In permafrost, soil samples from Siberia, scientists have discovered bacteria that remain metabolically active at minus 20 degrees Celsius and can even slowly reproduce at minus 10 degrees. They produce special antifreeze proteins that prevent ice crystals from forming inside their cells. Mars's subsurface temperatures, particularly near the equator at moderate depths, could range from minus 20 to plus 20 degrees Celsius, well within the range where Earth's psychrophiles thrive. If Martian life evolved similar cold adaptation mechanisms, it wouldn't need Mars to warm up. It could be living right now, in the cold, doing what Earth's psychrophiles do, persisting slowly, patiently in temperatures most organisms would find lethal. One of the most Mars-like environments on Earth is the Rio Tinto in Spain, a river that runs blood red due to its extreme acidity and high concentrations of dissolved iron. The pH of Rio Tinto averages around 2, about as acidic as stomach acid. This acidity comes from the metabolism of iron-oxidizing bacteria that live in the river, breaking down iron sulfide minerals and producing sulfuric acid as a byproduct. Despite the acidity, despite the heavy metal concentrations that would be toxic to most life, the Rio Tinto hosts a thriving microbial ecosystem. These acidophiles have adapted cell membranes and proteins that function in extreme acidity. Scientists have used Rio Tinto as a testing ground for instruments designed to detect life on Mars, because if our life detection technology can find microbes in Rio Tinto's harsh chemistry, it might stand a chance on Mars. What's remarkable about all these extremophiles isn't just that they survive in harsh conditions. It's that they don't just survive, they require those conditions. Take thermophiles, heat-loving microbes that live in hot springs and hydrothermal vents. Many thermophiles die if you cool them down to room temperature. The extreme environment isn't a hardship they endure, it's their optimal habitat. This flips our intuition. We think of extreme environments as hostile as places life has to struggle against. But to a thermophile, a boiling hot spring is paradise. To a halophile, salt is safety. To an acidophile, pH 2 is just right. Which makes you wonder if Martian life exists. Does it consider Mars harsh? Or is Mars, with its thin air and cold temperatures and perchlorate salts, exactly what that life needs to thrive? There's a concept in biology called the Goldilocks zone, the range of conditions that are just right for life. We usually apply this to astronomy, the distance from a star where liquid water can exist on a planet's surface. But there's also a biochemical Goldilocks zone, and extremophiles have shown us that this zone is much, much wider than we thought. Life on Earth has adapted to temperatures from minus 25 to plus 122 degrees Celsius pH levels, from to 13 pressures from near vacuum to over 1,000 atmospheres, and salinity from distilled water to saturated brine. That's an enormous range. And every time we discover life in a new extreme, the range expands further. We keep finding the boundaries of life, and life keeps pushing them back. In 2020, researchers announced the discovery of microbes living in sediment cores, taken from beneath 75 meters of seafloor in deposits that are 101 million years old. These microbes weren't fossils. They were alive, or at least metabolically active, having persisted in a near-starvation state for over 100 million years. They divided perhaps once every 1,000 years, subsisting on traces of organic matter and whatever energy they could scavenge from their environment. 100 million years. That's longer than the entire age of the dinosaurs. It's a timescale so vast it's almost geological. And yet these organisms endured cell-by-cell generation by glacial generation. If Earth microbes can survive 100 million years buried in seafloor mud, what might Martian microbes have survived in subsurface ice or aquifers over the 4 billion years since Mars's surface became uninhabitable? The lesson from extremophiles isn't that life is indestructible, it's that life is creative. Evolution doesn't solve problems with a single solution. It explores every possible solution, trying different biochemistries, different strategies, different adaptations. And given enough time, given enough generations, life finds ways to exist in places we thought were impossible. Mars might not have forests or oceans anymore, but it has niches places where temperature pressure, chemistry, and water availability overlap in ways that to the right organism might be livable. And if Earth's extremophiles teach us anything, it's that livable is a far broader category than we once believed. Have you ever considered that we might be the extremophiles' Earth's surface with its 21% oxygen atmosphere is actually an extreme environment? Oxygen is highly reactive, corrosive even. Early life on Earth lived in an oxygen-free world and had to develop complex antioxidant systems when oxygen-producing cyanobacteria changed the atmosphere. For many modern anaerobic bacteria, oxygen is poison. They die in its presence. To them, we live in a toxic, oxygen-saturated hellscape, but we call it home. Which raises the question, if we ever meet Martian life, will it see Mars the way we see Earth? Will it find our planet's thick atmosphere and abundant water as alien and hostile as we find Mars's thin air and frozen deserts? The extremophiles of Earth aren't just curiosities, they're blueprints. They show us the molecular mechanisms, the biochemical tricks, the evolutionary innovations that make survival possible in conditions we once called incompatible with life. And every mechanism we discover, the antifreeze proteins, the salt-balancing solutes, the cryptobiotic suspension, the chemosynthetic metabolism, is a mechanism that Martian life could in theory have independently evolved. Life doesn't need Earth. It just needs the right chemistry, the right energy source, and enough time to figure out how to use them. Mars had water chemistry in 4 billion years. That's a long time for evolution to work. The question isn't whether it's possible. The question is whether it happened. And there's one more piece to this puzzle, one more place where Mars might still hold liquid water, still maintain environments where extremophile-like organisms could theoretically survive. That place isn't on the surface visible to rovers and cameras. It's beneath the ice in the hidden reservoirs that radar has glimpsed but never touched. It's in the subsurface where pressure and geothermal warmth might conspire to keep water liquid even in the coldness of modern Mars. That hidden water, those underground possibilities are what we explore next. The secret oceans that might flow even now beneath the red dust. What if Mars isn't as dead as it looks? What if beneath the rust-colored dust and frozen plains there are rivers that still flow, lakes that still hold reservoirs of water waiting in the dark? We've been talking about ancient Mars, about water that existed billions of years ago. But the story doesn't end there. Mars has water now. Not on the surface where we can easily see it, but hidden, locked away in ice and possibly flowing in places we've only begun to understand. And where there's water, even hidden water, there's a possibility that makes everything we've discussed suddenly feel more urgent, more real. In 2008, the Phoenix lander touched down near Mars's North Polar region with one primary mission dig. On its 5th Martian day, Phoenix's robotic arm scraped away the top layer of rust-colored soil and exposed something that gleamed white in the photographs sent back to Earth. Ice. Pure water ice, sitting just 3 inches beneath the surface. Over the following days, as the Martian sun warmed the trench Phoenix had dug, that ice sublimated turned directly from solid to vapor, disappearing into the thin atmosphere. It was the first direct confirmation that Mars has accessible water ice near its surface, not ancient fossil ice from billions of years ago, but ice that exists right now, cycling through Mars's present-day climate system. Phoenix had essentially confirmed what orbital radar had suggested. Mars's polar regions and mid-latitudes are rich with subsurface ice, sometimes comprising up to 50% or more of the volume of the upper few meters of soil. The Mars Reconnaissance Orbiter carries an instrument called Shared Shallow Radar, which can penetrate several hundred meters below the Martian surface and detect layers of different materials based on how radio waves reflect back. SHARAD has mapped vast sheets of buried ice across Mars's mid-latitudes ice deposits that extend for miles and are tens to hundreds of meters thick. These aren't small pockets of frost. They're glaciers essentially buried under a protective layer of dust and rock. Some of these buried glaciers show flow features, ridges, and grooves, suggesting that at some point in Mars's recent geological past, they were moving slowly flowing like glaciers on Earth. They're dormant now, frozen in place, but they're there. Imagine standing on Mars, drilling down a few meters and hitting not rock, but solid ice stretching deeper than you can measure. It's Antarctica beneath a desert memory written in frozen water. But ice, while promising, is still frozen. Liquid water is what life needs, at least life as we know it. And this is where Mars gets complicated, where the evidence becomes tantalizing, but frustratingly ambiguous. Starting in 2011, scientists analyzing high-resolution images from the Mars Reconnaissance Orbiter noticed something peculiar: dark streaks that appeared on steep slopes during warm seasons and faded during cold seasons. They called them recurring slope lineae, or RSL for short. These streaks are narrow, typically a few meters wide, and can be hundreds of meters long. They appear on sun-facing slopes when temperatures rise above minus 23 degrees Celsius, which is the temperature at which briny water saturated with salts could theoretically remain liquid under Martian atmospheric pressure. When temperatures drop, the streaks fade. The pattern repeats annually like a Martian spring thaw and winter freeze, except it's not water, ice melting. It seems to be something else, something involving salts. The leading hypothesis is that RSL are caused by briny water, specifically water mixed with perchlorate salts, which are abundant in Martian soil. Perchlorates dramatically lower the freezing point of water. A concentrated perchlorate solution can remain liquid at temperatures as low as minus 70 degrees Celsius, well within the range of Mars's seasonal temperature swings. The idea is that subsurface ice melts when warmed by the sun, mixing with perchlorate salts in the soil, and the resulting brine seeps downslope under gravity, darkening the soil as it flows. When temperatures drop, the brine refreezes or evaporates, and the dark streak fades. It's elegant, and it fits the observations. But here's the complication: spectroscopic analysis of RSL hasn't definitively detected water. Some studies have found signatures of hydrated salts, which suggests water was present at some point. Others found no clear water signature at all. It's possible the water evaporates too quickly to be detected from orbit, or that the brines are too salty for current instruments to identify water within them, or that RSL aren't caused by liquid water at all, but by some other process like flowing sand or sublimating carbon dioxide frost, creating avalanches. The debate is ongoing, careful, and characterized by scientific caution. What everyone agrees on is that something is happening on those slopes, something seasonal and dynamic. What exactly it is remains one of Mars's most intriguing mysteries. In 2018, researchers using the Marcis radar instrument aboard the European Space Agency's Mars Express orbiter announced something extraordinary. They had detected a bright reflection in radar data from beneath the South Polar ice cap, specifically under a region called Planum Australe. The reflection was exactly what you'd expect from a body of liquid water, strong and continuous over an area about 12 miles across, located roughly a mile beneath the ice. The scientists were cautious in their announcement, noting that the interpretation depended on assumptions about ice composition and temperature. But if correct, this would be Mars's first confirmed subsurface lake, a reservoir of liquid water existing right now, hidden beneath polar ice, kept liquid by a combination of pressure from the overlying ice geothermal heat from below, and almost certainly high concentrations of dissolved salts, particularly perchlorates and calcium perchlorate, which act as antifreeze. Liquid water on Mars. Not ancient, not theoretical, but present. Subsequent studies using the same radar data found additional bright reflections nearby, suggesting not just one lake, but possibly several smaller bodies of water. A network of subglacial lakes, similar to those found beneath Antarctica's ice sheets on Earth. Lake Vostok, buried under 2.5 miles of ice in Antarctica, has been isolated from the surface for potentially 15 million years. Yet when Russian scientists finally drilled into it, in 2012 they found microbial life. If Antarctic subglacial lakes can harbor life in isolation, why not Martian ones? The comparison is compelling, but not perfect. Mars's lakes, if they exist, would be far saltier than Lake Vostok, possibly saturated with perchlorates to concentrations that would challenge even Earth's most salt-tolerant microbes. And we can't directly verify the lakes yet. Radar gives us strong evidence, but only drilling could confirm them definitively. Still, the possibility remains hanging there in the data liquid water beneath the ice right now. Let's talk about the stability of that water. On Mars's surface, liquid water can't persist. The atmospheric pressure averaging around 600 pascals is below the triple point of water, the pressure and temperature at which water can exist as solid liquid and gas simultaneously. Below the triple point, water ice sublimates directly to vapor without melting, and any liquid water that somehow forms immediately boils away. But underground pressure increases with depth. At a depth of just a few hundred meters, pressure becomes sufficient for liquid water to exist, if the temperature is right. And Mars, despite its cold surface, has geothermal heat. The planet's core is still molten, and heat flows outward, warming the deeper layers. Models suggest that at depths of several kilometers, temperatures could be warm enough for liquid water even without salts. Add salts to depress the freezing point, and liquid water becomes possible at shallower depths, maybe even a kilometer or two, down places that aren't completely beyond reach of future drilling missions. There's a region on Mars called Cerberus Fossae, a series of fissures that cut across the Elysium Planitia plain. In 2020, scientists analyzing very recent orbital imagery noticed something strange. These fissures appeared to have been active within the last 10 million years, possibly much more recently, depositing layered sediments that look suspiciously like they were laid down by flowing water. But Mars has been cold and dry for billions of years. Where would water come from to create these deposits? One hypothesis is that Mars experiences episodic releases of subsurface water, perhaps when volcanic activity or tectonic shifts crack through to underground aquifers, allowing pressurized water to breach the surface temporarily before freezing or evaporating. These would be brief events, geological hiccups, but they'd leave evidence. And that evidence is what researchers think they're seeing in places like Cerberus Fossae. Mars might have underground water reservoirs that very occasionally breach the surface. It's not a steady flow, it's more like a punctuated equilibrium, long periods of stasis interrupted by brief moments of release. Consider the seasonal cycle of Mars's polar ice caps. The caps are composed of two types of ice water, ice and carbon dioxide, ice also called dry ice. In winter, carbon dioxide from the atmosphere freezes onto the polar cap, coating it in a layer of dry ice several meters thick. In summer, that carbon dioxide sublimes back into the atmosphere, and the cap shrinks, revealing the permanent water ice underneath. The Mars Odyssey spacecraft has mapped this cycle in exquisite detail, watching the caps grow and shrink over multiple Martian years. During peak summer, the North Polar Cap loses most of its carbon dioxide ice, exposing water ice that remains year-round. The South Polar Cap retains more carbon dioxide, but even there, patches of water ice peek through. These seasonal changes represent a massive transfer of material, carbon dioxide, equivalent to 25% of Mars's entire atmosphere, freezes out every winter and sublimates every summer. It's a planetary respiration, Mars breathing in and out with its seasons. But here's what intrigues scientists: the polar caps aren't just ice sitting on rock. They're layered with alternating bands of ice and dust that record Mars's climate history, much like tree rings record Earth's. These layers, called polar layered deposits, extend several kilometers deep and represent millions of years of accumulation. They formed because Mars's axial tilt, its obliquity, changes significantly over time scales of tens of thousands to hundreds of thousands of years. Earth's axial tilt stays relatively stable, varying only between 22.1 and 24.5 degrees, thanks to the stabilizing influence of our large moon. Mars without a large moon wobbles more dramatically, its axial tilt varying between about 15 and 35 degrees. When the tilt increases, summers become warmer and winters become colder, causing more ice to sublimate from the poles and redistribute toward the equator. When the tilt decreases, the poles get colder and accumulate more ice. Each cycle leaves a layer, a record of climate oscillation, frozen in time. Reading these layers is like reading a book of Martian climate history, and scientists are only just learning to interpret it. During periods of high obliquity, when Mars's tilt was steep and its poles were warmer, some models suggest that subsurface ice at mid-latitudes could have partially melted, creating temporary aquifers that fed springs or even short-lived lakes on the surface. These wouldn't last long, maybe a few years or decades before refreezing, but they'd be enough for liquid water to briefly exist on the surface, possibly even in volumes large enough to support microbial life, if any existed underground. It's a cyclical pattern. Mars warms slightly. Ice melts, water flows, conditions become temporarily habitable. Then the cycle reverses and everything freezes again. Life, if it exists on Mars today, would have to be adapted not just to extreme conditions, but to cyclical conditions able to bloom during the brief warm periods and survive dormancy during the long freezes. It's harsh, but again, Earth has analogs. Permafrost microbes do this. They've been doing it for hundreds of thousands of years. One of the most important discoveries about Martian water came from analyzing the isotopic composition of water vapor in Mars's atmosphere. The Mars Curiosity rover and orbiting spectrometers have measured the ratio of deuterium heavy hydrogen to normal hydrogen in Martian water. Deuterium is about twice as heavy as normal hydrogen, and because lighter hydrogen escapes into space more easily, a planet that has lost a lot of water over time will have an enriched deuterium to hydrogen ratio in whatever water remains. Mars's ratio is about 5 to 7 times higher than Earth's ratio, and about 8 times higher than the ratio measured in Martian meteorites, which represent ancient Martian water from billions of years ago. This tells us that Mars has lost a substantial amount of water to space over geological time, but it also tells us how much might remain. By comparing ancient and current ratios, scientists estimate that Mars once had enough water to cover its entire surface in an ocean at least 100 to 450 feet deep, possibly much more. Most of that water is gone, but not all of it. Some remains buried in ice, trapped in minerals, possibly flowing in deep aquifers. Mars didn't lose everything. It just hid what it had left. There's a poetic irony here. We spend so much effort trying to find liquid water on Mars because water is essential for life, yet Mars might have vast reserves of water that are simply inaccessible to us right now. It's not that the water isn't there, it's that it's locked away, frozen or buried or dissolved in brines. So salty we're not sure even the hardiest Earth microbes could tolerate them. It's frustrating, but it's also hopeful. Because if water exists now beneath the surface in stable environments, protected from radiation and temperature extremes, then those environments could in theory support life. Not life that we'd easily find, not life that would wave hello to a passing rover, but life that persists quietly in the dark in pockets of brine or meltwater, microbial communities that have been there for millions of years, unnoticed and unaffected by the surface world's transformation into a frozen desert. This raises a critical question for future Mars exploration. Where do we drill? If we want to find liquid water, or more importantly, to test whether that water might contain life, we need to know where to aim our drills. The polar lakes detected by radar are tantalizing but challenging. They're a mile beneath solid ice, which would require drilling technology we haven't yet deployed on Mars. The recurring slope lineae are dynamic and accessible, but the potential brines are probably very salty, and we'd need to time a mission to arrive during the active season. Mid-latitude buried glaciers are closer to the surface and extensive, but are they entirely frozen, or are there pockets of liquid water at their bases, where pressure and geothermal heat might create melt zones? Every target has trade-offs between scientific promise and technical difficulty. And underlying all these considerations is the principle of planetary protection. If we drill into a subsurface aquifer and find life, we need to be absolutely certain we didn't bring that life with us from Earth on contaminated equipment. It's a problem that requires sterility standards even more rigorous than those used in medical surgery. Have you ever thought about what it would mean to drink Martian water? Not the salty brine, not the perchlorate-laden liquid, but pure Martian ice melted and filtered. Would it taste different from Earth water? Chemically, H2O is H2O, but dissolved gases and trace minerals give water its taste. Martian water formed billions of years ago, frozen and buried, containing minerals leached from Martian rock, would carry a different signature, a different mineral profile. It would taste quite literally of another world. Future astronauts will almost certainly drink Martian water. Extracting it from subsurface ice is far easier than transporting water from Earth. And in that moment, when the first human drinks water that fell as rain on ancient Mars, there will be a connection across time, a closing of the loop between past and present, between the Mars that was and the Mars that is. But water isn't just a resource or a potential habitat. Water is also evidence. It's a story written in hydrogen and oxygen atoms, a record of where Mars has been and what it has lost. Every isotope measurement, every ice core, every subliming frost is a page in that story. And we're still learning to read it, slowly assembling the narrative from fragments. The water that exists on Mars today is the memory of oceans that no longer lap against shores of rivers, that no longer carve valleys of rain, that no longer fall softly on red soil. It's a memory crystallized into ice, dissolved into brine, locked into minerals. And if life exists in that water, it would be the memory of something else, of the moment when chemistry became biology, when Mars was young enough and warm enough for that transformation to occur. That's what we're searching for. In the ice and brine, not just water, but memory. Not just chemistry, but maybe the fading echo of life. Yet water, for all its importance, doesn't exist alone on Mars. It exists within a chemistry that challenges our assumptions, a set of elements and compounds that could support life or destroy it, depending on perspective. The soil beneath the ice, the salts in the brine, the thin atmosphere that both protects and exposes all of these create an environment unlike anything on Earth. And understanding that environment, learning its chemical language, is essential before we can truly know whether Mars is habitable, was habitable, or might be habitable again. That chemistry, strange and toxic and possibly life-giving all at once, is where we turn now. Imagine standing on Mars with a handful of soil. It looks harmless, just rust-colored dust. But that dust contains chemicals that would burn organic tissue salts that draw water out of cells and compounds that to most Earth life are poison. And yet, here's the twist. Those same chemicals might be exactly what Martian life would need to survive. Toxicity isn't absolute, it's perspective. What kills one organism feeds another. And understanding Mars's chemistry means learning to see poison as potential danger, as opportunity, and obstacles as the very conditions that life, if it's there, has learned to call home. When the Phoenix lander analyzed Martian soil in 2008, it found something unexpected. Perchlorate salts, specifically calcium and magnesium, perchlorate in concentrations of about 0.4 to 0.6% by weight. That might not sound like much, but it's significant. Roughly 4,000 to 6,000 parts per million. For comparison, the EPA's safe limit for perchlorate in Earth drinking water is 15 parts per billion. Mars soil has concentrations hundreds of thousands of times higher. Perchlorates are oxidizing agents, meaning they readily give up oxygen atoms in chemical reactions. They're used in rocket fuel fireworks and explosives precisely because of this property. When living cells encounter high concentrations of perchlorates, the compounds can disrupt thyroid function and damage cellular structures. They're classified as environmental contaminants on Earth. On Mars, they're everywhere, mixed thoroughly into the soil by billions of years of dust storms redistributing material across the planet's surface. But here's what makes perchlorates fascinating. Rather than just problematic, some Earth bacteria can actually metabolize them. These organisms, called perchlorate-reducing bacteria, use the compound as an electron acceptor in their metabolism, breaking down perchlorate to access the oxygen atoms and using that oxygen to burn organic molecules for energy, much like how we use atmospheric oxygen when we breathe. These bacteria were discovered in contaminated groundwater near rocket fuel manufacturing sites, places where perchlorate pollution was killing most life, but where these specialized microbes thrived. They evolved or perhaps already possessed enzymes that could safely handle perchlorate chemistry, turning a toxin into food. If Earth bacteria independently evolved this capability relatively quickly in response to human contamination, might Martian life have evolved similar mechanisms over billions of years in an environment naturally rich with perchlorates? It's not just possible, it's biochemically plausible. The Phoenix lander conducted an experiment called the Wet Chemistry Lab, mixing Martian soil with water and measuring the pH and dissolved ions. The results showed the soil was slightly alkaline with a pH around 7.7 to 8.3 and contained various salts, including not just perchlorates, but also magnesium, sodium, potassium, and chloride ions. This wasn't the harsh acidic environment some scientists had expected. It was surprisingly rather mild, salty, yes, and with unusual chemistry, but not inherently hostile to life in the way that, say, concentrated sulfuric acid would be. The team even joked that you could theoretically grow asparagus in Martian soil if you added water and nutrients, though they acknowledged you'd probably want to wash out the perchlorates first. The point stands, though. Martian soil isn't sterile alien material. It's soil-recognizable soil, just with a different mineral composition shaped by different geological history. Radiation is Mars's other major chemical challenge, though it's physics rather than chemistry per se. Without a thick atmosphere or a global magnetic field, Mars's surface is exposed to cosmic radiation and solar energetic particles at levels far higher than Earth experiences. The Curiosity rover carries a radiation detector called RAD, the Radiation Assessment Detector, which has been measuring the radiation environment since landing in 2012. The data shows that Mars's surface receives about 0.67 millisieverts of radiation per day. That accumulates to roughly 240 millisieverts per year. For comparison, the average person on Earth receives about 2.4 millisieverts per year from natural background radiation, and astronauts on the International Space Station receive about 150 millisieverts per year. Mars's surface, in other words, has a radiation environment more than 80 times higher than Earth's surface and significantly higher than even low Earth orbit, because the ISS benefits from Earth's magnetic field providing some shielding. This radiation isn't uniform or constant. During solar storms, energetic events when the sun ejects massive clouds of charged particles, radiation levels on Mars spike dramatically. In September 2017, a series of powerful solar flares increased radiation levels detected by RAD by more than 50 times for several hours. These solar particle events are unpredictable and potentially deadly to any unprotected life on the surface. But here's the thing. Radiation intensity decreases rapidly with depth. Just 1 meter below the Martian surface, radiation drops to levels comparable to those in low Earth orbit. At depths of several meters, it decreases to near Earth surface levels. This means that subsurface habitats, whether for human colonists or hypothetical microbial life, would be naturally protected from radiation simply by being underground. Surface life on modern Mars is essentially impossible without extraordinary radiation resistance or protective mechanisms. Subsurface life faces a much gentler environment. Some Earth organisms have evolved remarkable radiation resistance. Deinococcus radiodurans, nicknamed Conan the bacterium, can survive radiation doses of up to 5,000 grays. A dose of 5 grays is lethal to humans. Deinococcus radiodurans can withstand 1,000 times that amount and continue functioning. It does this through multiple redundant copies of its genome and extremely efficient DNA repair mechanisms that can reconstruct shattered chromosomes from fragments within hours. When researchers exposed Deinococcus radiodurans to simulated Mars conditions, low pressure, cold temperatures, high radiation, it survived for extended periods, though its survival rate decreased over time. But it survived. If Earth life can evolve this level of radiation resistance, there's no fundamental reason Martian life couldn't have evolved similar or even more effective mechanisms, especially if it spent billions of years adapting to a gradually worsening radiation environment as Mars's magnetic field died and atmosphere thinned. Mars's atmosphere itself presents a complex chemistry problem. At 95% carbon dioxide, it's not breathable by Earth standards, and its extreme thinness means there's almost no buffering against temperature swings or meteorite impacts. But carbon dioxide is a resource. Plants photosynthesize using CO2, and some bacteria can fix carbon dioxide directly from the air without photosynthesis using chemical energy instead of sunlight. On Mars, with its abundant atmospheric CO2, carbon wouldn't be a limiting resource for life. Energy would be the bottleneck. Without sunlight penetrating underground or abundant organic matter to consume any subsurface, Martian ecosystem would need to rely on chemosynthesis, deriving energy from chemical reactions between minerals and water, exactly like Earth's deep subsurface and deep ocean vent communities do. Dust storms on Mars deserve special attention because they're not just weather, they're a planetary-scale chemical and physical phenomenon that reshapes the environment. Martian dust is incredibly fine, with particles averaging about 3 micrometers in diameter, smaller than talcum powder. During storms, this dust becomes electrostatically charged through friction, and it's lifted into the atmosphere, where it can remain suspended for weeks or months. Local dust storms occur frequently, but roughly every 3 Martian years, about 5.5 Earth years, conditions align for a global dust storm that envelops the entire planet. The most recent global storm occurred in 2018, and it's what killed the Opportunity rover after 14 years of operation. The 2018 dust storm began in late May as a localized storm near Opportunity's location in Perseverance Valley. Within weeks, it had grown to encompass the entire planet, blocking out so much sunlight that Opportunity, which relied on solar panels for power, couldn't generate enough electricity to stay active. The rover sent its last communication on June 10, 2018, and despite NASA's months-long recovery efforts, it never woke up again. The dust blocking sunlight wasn't the only problem. The storm also caused temperature fluctuations that likely stressed Opportunity's aging electronics, and the dust itself probably coated the solar panels so thoroughly that even when the storm cleared, insufficient light could reach the cells. It was a death by environmental overwhelm, the planet itself reclaiming a machine that had lasted far longer than its planned 90-day mission. But here's what's fascinating about that dust storm from a chemistry perspective. Even though it blocked most sunlight, making the surface dark as twilight. For months, the dust itself didn't settle quickly because Martian atmospheric conditions kept it aloft. The dust particles charged and tiny interacted with each other, and with the trace amounts of water vapor in the atmosphere, possibly forming tiny aggregates or even transient water ice coatings at night when temperatures dropped. Some researchers have suggested that these dust particles coated with ice and mixed with perchlorates and other salts might create microscopic environments where chemical reactions could occur. Reactions that might even produce organic compounds in the atmosphere. The chemistry of Martian dust storms is still poorly understood, but its complex dynamic and potentially relevant to questions about organic chemistry and prebiotic molecules on Mars. The dust itself is chemically reactive. Martian dust contains iron oxides, the rust that gives Mars its color, as well as sulfates, chlorides, and those ubiquitous perchlorates. When the Phoenix lander heated soil samples to analyze them, the perchlorates decomposed at high temperatures, releasing oxygen gas and chlorine compounds. Some of these chlorine compounds reacted with any organic molecules present, potentially destroying evidence of organics that scientists were trying to detect. This created a problem. Mars rovers carry instruments that heat soil to analyze its chemistry, but the heating process itself might be destroying the very organic molecules they're searching for. It's a methodological catch-22. The Curiosity and Perseverance rovers have tried to work around this by using lower temperatures and different analytical techniques, but the perchlorates remain a challenge. They're both potentially useful as an oxygen source or energy source for life, and problematic as an analytical interference. There's a chemical called hydrogen peroxide H2O2 that's commonly used on Earth as a disinfectant. It's reactive, breaking down into water and oxygen, and in the process it damages cellular structures and DNA. Some researchers have proposed that Martian soil might contain hydrogen peroxide or related oxidizing compounds generated by UV radiation interacting with the thin atmosphere and perchlorates in the soil. This would make Martian soil not just salty, but actively oxidizing, capable of breaking down organic molecules on contact. It's one explanation for why Viking's organic detection experiments in 1976 found nothing. If the soil itself was oxidizing, it would have destroyed organics long before they could be detected. But again, oxidizing environments aren't necessarily lifeless. Earth has oxidizing environments, and life has adapted. The question isn't whether Mars's chemistry is harsh. It is. The question is whether it's uniquely harsh in ways that make life impossible, or just different in ways that would require different adaptations. Temperature swings on Mars are extreme because of the thin atmosphere's inability to retain heat. At the equator, during summer, daytime temperatures can reach 20 degrees Celsius, about room temperature, but at night, they plummet to minus 70 degrees Celsius or colder. That's a swing of 90 degrees Celsius in a single day. For comparison, the largest daily temperature swing on Earth in deserts like the Sahara is about 40 degrees Celsius. Most Earth organisms couldn't survive being frozen solid every night and thawed every morning, but some can. Antarctic microbes experience freeze-thaw cycles regularly and have evolved antifreeze proteins and mechanisms to prevent ice crystal formation inside cells. If Mars ever had life, it would need similar adaptations, plus the ability to handle rapid, repeated freezing and thawing on a daily basis for millions or billions of years. It's not impossible, but it's demanding. The combination of all these factors perchlorates radiation. Dust temperature swings, oxidizing chemistry, creates what scientists call a multiple stressor environment. Each stressor alone might be manageable. Life on Earth handles radiation, cold salinity, and oxidation separately in different extreme environments. But Mars combines them all simultaneously. A Martian microbe, if it exists, would need to be radiation-resistant and cold-adapted and salt-tolerant, and capable of metabolizing unusual chemistry all at once. That's a tall order. Yet extremophiles on Earth show us that life can stack adaptations, that organisms can be both thermophilic and acidophilic, or both halophilic and radiation resistant. Life is modular in its survival strategies. There's no fundamental law saying that all these adaptations can't coexist in a single organism. It's just that we haven't found an Earth organism that needs all of them simultaneously, because Earth doesn't have a Mars-like environment. Do you think poison depends on who's doing the tasting? On-Earth oxygen, the gas we breathe and need to survive, was originally toxic to early life. When cyanobacteria began producing oxygen through photosynthesis about 4 billion years ago, it caused the Great Oxidation Event, a mass extinction of anaerobic organisms that couldn't tolerate oxygen's reactivity. The organisms that survived either adapted developing antioxidant systems and metabolisms that could handle or even exploit oxygen, or they retreated to oxygen-free environments where they persist today. To them, our oxygen-rich world is toxic. To us, it's life. Mars's perchlorates and oxidizing soil might look like poison from our perspective, but from a Martian microbe's perspective, if such a thing exists, it might be exactly what's needed. Home doesn't have to be gentle. It just has to be consistent. There's a subtle point here about habitability that often gets lost in discussions about Mars. Habitability doesn't mean comfortable. It means capable of supporting life. And life is remarkably flexible in its requirements. What life absolutely needs, as far as we know, is liquid water, organic molecules, or a source of carbon energy to drive metabolism and time. Mars has had all of these at various points in its history, and it still has some of them. Now, water and ice, and possibly liquid brines, carbon dioxide, and abundance chemical energy from rock-water interactions, and 4 billion years of time. The chemistry is harsh, yes, but harsh isn't the same as impossible. It's just selective. It means that if life exists on Mars, it won't look like Earth life in its environmental preferences. It'll be adapted to Mars shaped by Martian conditions into something that can only thrive there. This raises an important consideration for future human exploration. If we send astronauts to Mars, they'll need protection not just from radiation and cold, but from the soil itself. Perchlorate dust brought into habitats on spacesuits could contaminate water supplies and food. Breathing Martian dust would expose lungs to oxidizing compounds and fine particles that could cause respiratory damage. Engineers designing Mars habitats need to include airlocks with decontamination and protocols, systems for washing, perchlorates out of water, and shielding to protect against radiation. Mars isn't inherently hostile to humans in the sense of being actively trying to kill us, but it's deeply indifferent, and its chemistry operates by rules that don't account for Earth biology's vulnerabilities. We'll need to account for them ourselves. Yet this same challenging chemistry is also full of resources. Perchlorates contain oxygen that can be extracted for breathing air or rocket fuel. Carbon dioxide can be split into oxygen and carbon monoxide using electricity. Water ice can be melted purified and used for drinking agriculture or electrolysis into hydrogen and oxygen for fuel. Iron in the soil could be processed into metal for construction. Martian chemistry is harsh, but it's also rich with raw materials. Turning Mars into a place where humans can live will require understanding its chemistry deeply enough to know not just what's dangerous, but what's useful, what can be transformed, what can be exploited. It's alchemy of a sort, not turning lead into gold, but turning Martian dust and ice into breathable air and drinkable water. The dust storms, for all their destructiveness, also reveal something about Mars's present-day dynamism. This isn't a completely dead world geologically frozen in time. Mars has weather seasonal changes, active chemistry in the atmosphere and soil, and ongoing surface processes. The planet is quieter than Earth, less violent, slower in its changes, but it's not static. And wherever there's change, wherever energy flows and chemistry happens, there's the potential for complexity. That's what we're looking for, not just life, but complexity, organization, and chemistry that's doing something more than just reaching equilibrium. Life is chemistry that resists equilibrium, that builds structure, and maintains it against entropy. Mars's chemistry creates challenges for that kind of complexity, but Challenges aren't barriers, they're just obstacles that evolution, given enough time, might find ways around. Behind every rover, every lander, every orbital spectrometer analyzing Martian chemistry, there are humans. Scientists and engineers who've devoted careers to understanding this one red planet. People who've felt crushing disappointment when missions failed, exhilaration, when discoveries exceeded expectations, and patient determination through years of ambiguous results. The chemistry of Mars is fascinating in itself, but the human element, the persistence, the curiosity, the willingness to spend decades asking questions that might not have clear answers, that's what transforms data into meaning. And it's to those human stories, those missions, and the people behind them that we turn next. Because understanding Mars isn't just about rocks and chemistry. It's about us, about what it means to reach across space toward another world and refuse to stop reaching even when the answers remain hidden in dust. Every robot we've sent to Mars carries something invisible with it, human hope. Behind every photograph of red soil, every measurement of atmospheric pressure, every sample drilled from ancient rock, there are people engineers who stayed up nights troubleshooting code, scientists who spent careers interpreting Pixel's mission, controllers who spoke to machines millions of miles away as if they were beloved children. Mars exploration isn't just a story of technology. It's a story of persistence, heartbreak, triumph, and the stubborn human refusal to accept that some questions should remain unanswered. And sometimes the failures teach us more than the successes ever could. July 14th, 1965. Mariner 4 completed its flyby of Mars and began transmitting the first close-up images of another planet ever captured. The science team gathered around a teletype printer that was slowly, line by line, printing numbers representing pixel brightness values. They couldn't wait for the full image processing, so they went to an art supply store, bought colored pencils, and hand-colored the numbers on a strip of paper taped to the wall. Dark colors for low numbers, light colors for high numbers. What emerged from those hand-colored numbers was devastating. Craters. Just craters. A dead moon-like surface where many had hoped to see canals, vegetation, or at least something suggesting a living world. One scientist later recalled the mood in the room as funereal. Mars, it seemed, was not the Mars of imagination. It was cold, cratered, and utterly barren. The dream had crashed against reality, and reality had won. But Mariner 4 only photographed about 1% of Mars's surface, a narrow strip during a brief flyby. It was like judging all of Earth based on photographs of the Sahara Desert or Antarctica. Yet that limited glimpse shaped Mars science for years, orienting expectations toward a dead planet and making subsequent discoveries of ancient water and potentially habitable environments all the more surprising. It's a reminder that first impressions, even in science, can mislead. What we see first isn't necessarily what's true, it's just what we've seen so far. Patience and persistence reveal the rest. The Viking program in 1976 represented humanity's first successful landing on Mars, and our first attempt to directly search for life. Two identical spacecraft, Viking 1 and Viking 2, each consisting of an orbiter and a lander, arrived at Mars with ambitious goals. The landers carried 3 biological experiments specifically designed to detect metabolic activity photosynthesis, or organic molecules, signatures of life. One experiment, the gas exchange experiment, added nutrients to Martian soil and monitored for gases that microbes might release. Another, the labeled release experiment, added radioactive nutrients and tested whether organisms would metabolize them and release radioactive carbon dioxide. The third, the pyrolytic release experiment, exposed soil to radioactive carbon dioxide and then heated it to see if the carbon had been incorporated into organic molecules. The results were confusing. The labeled release experiment returned positive results. When nutrients were added to Martian soil, radioactive CO2 was released rapidly, exactly what you'd expect from biological metabolism. The pattern was reproducible. But when the soil was sterilized by heating before the test, the reaction stopped, which is also consistent with biology. Heat kills organisms. Gilbert Levin, the experiment's principal investigator, believed he had detected life on Mars. But another Viking instrument, the gas chromatograph mass spectrometer, designed to detect organic molecules, found nothing. No organics at all in the Martian soil. How could there be metabolism without organic molecules? How could life exist without leaving organic traces? The scientific consensus settled on a non-biological explanation. Reactive chemicals in the Martian soil, possibly including perchlorates and superoxides, were mimicking biological metabolism. But Levin maintained until his death in 2021 that Viking had detected life and that the lack of organics was an instrumental limitation, not proof of absence. We still don't know for certain. Viking's ambiguous results remain one of the most debated topics in Mars science nearly 50 years later. Let's talk about failure, because Mars has a way of humbling even the best engineers. In 1999, NASA lost 2 spacecraft within months of each other. The Mars Climate Orbiter approached Mars in September, fired its engines to enter orbit, and disappeared. Post-failure investigation revealed a catastrophic mistake. One team had programmed the spacecraft's thrusters using English units of pound-force seconds, while another team expected metric units of Newton seconds. The spacecraft's trajectory calculations were off by a factor of 4.45, causing it to approach Mars far too closely. It either burned up in the atmosphere or skipped off into space. Either way, it was gone, and $327 million worth of mission along with it lost, because someone forgot to convert units. It's the kind of mistake you might make on a high school physics problem, except this was a planetary spacecraft. The loss was embarrassing, painful, and entirely preventable. 3 months later, in December 1999, the Mars Polar Lander descended toward Mars's south polar region. It was supposed to land, gently deploy instruments, and study the Martian climate and subsurface ice. Contact was lost during descent, and the lander was never heard from again. Post-failure analysis suggested that when the lander's legs deployed during descent, they created a brief mechanical vibration that triggered sensors indicating the spacecraft had touched down, causing the descent engines to shut off prematurely. The lander was still 40 meters above the surface. It fell and crashed. The lesson was brutal space exploration operates on razor-thin margins for error, and even tiny design oversights can cascade into total mission loss. There are no second chances when you're 140 million miles away. But failure breeds resilience. After the losses of 1999, NASA restructured its Mars program, implementing more rigorous review processes and adopting a follow-the-water strategy for future missions. This led to Mars Odyssey in 2001, which successfully entered orbit and has been operating for over 2 decades, making it one of the longest-serving spacecraft at Mars. Odyssey's primary mission was to map the distribution of chemical elements and minerals on Mars's surface, and it was Odyssey's instruments that first detected the widespread subsurface hydrogen signatures, indicating vast deposits of water ice in Mars's polar regions. Success returned built on the painful lessons of failure. In 2004, 2 rovers named Spirit and Opportunity landed on opposite sides of Mars. They were designed to operate for 90 Martian days, about 92 Earth days. Spirit lasted 6 years. Opportunity lasted 14. Together, they transformed our understanding of Mars from a place that might have once had water to a place that definitely had water for extended periods in environments that could have supported life. Spirit landed in Gusev Crater and found evidence of ancient hot springs and hydrothermal systems. Opportunity landed on Meridiani Planum and discovered hematite concretions nicknamed blueberries, small iron-rich spheres that form in the presence of liquid water. These weren't just hints of water. They were geological proof recorded in rock. Opportunity's journey is worth lingering on Because it's a story of endurance. The rover was designed to travel about 600 meters. It traveled over 45 kilometers marathon distance on another planet, crossing plains, climbing crater rims, descending into valleys. Its solar panels expected to accumulate dust and lose power within months were periodically cleaned by Martian dust devils, mini tornadoes that swept across the rover and blew dust away, rejuvenating the panels. It was luck, but poetic luck. Mars itself seemed to be helping the mission continue. Engineers joked that Opportunity had a guardian angel in the form of fortuitous wind patterns. The rover explored craters like Endurance Erebus and Victoria, each one revealing layers of sedimentary rock that recorded different epochs of Martian history. But every machine has limits, and Opportunities came in 2018 with the global dust storm. As dust accumulated and sunlight faded, the rover's power dropped until it could no longer operate. Engineers sent over 1,000 recovery commands over 8 months, hoping the rover would wake up once the storm cleared and sunlight returned. It never did. In February 2019, NASA declared the mission complete. The last message Opportunity sent translated into human terms by a journalist, though the rover obviously didn't say anything in words, was interpreted as something like, "My battery is low and it's getting dark." That phrase, more poetic than technical, resonated deeply. It captured not just the rover's status, but the emotional weight of saying goodbye to a machine that had exceeded every expectation that had become, in a sense, a beloved emissary on another world. Have you ever felt attached to a machine? The engineers who worked on Opportunity certainly did. They celebrated the rover's birthdays worried during communication. Blackouts felt pride when it achieved milestones. When Opportunity died, grown scientists cried. There were eulogies. People shared memories on social media. A rover, a piece of technology without consciousness or feeling, had somehow become more than its components. It represented human curiosity, determination, and the desire to reach beyond ourselves. Its loss was felt personally by thousands who'd never touched it, but had followed its journey. Curiosity rover landed in 2012 with a mission to assess Mars's habitability. Unlike Spirit and Opportunity, which were solar-powered, Curiosity carries a radioisotope thermoelectric generator, essentially a nuclear battery, that converts heat from decaying plutonium-238 into electricity. This means Curiosity can operate through dust storms and Martian winter without relying on sunlight. It can also power a full onboard chemistry laboratory, making it the most sophisticated science platform ever sent to Mars. Curiosity has drilled into rocks, analyzed their composition, measured atmospheric chemistry, tracked methane fluctuations, and found organic molecules in multiple locations. It's been operating for over a decade and has driven over 30 kilometers, slowly climbing Mount Sharp at the center of Gale Crater, reading the geological history written in its layered slopes. Curiosity is also lonely in a way. It carries a small piece of metal from the World Trade Center, recovered from the 9/11 attacks, and incorporated into one of its instruments as a memorial. It sings "Happy Birthday" to itself every year on the anniversary of its landing, a brief musical tone from its actuators, the only sound it makes besides the whir of wheels and drills. These human touches, these small acts of commemoration and sentiment, remind us that exploration is never purely technical. We send our values, our memories, our capacity for meaning-making along with our machines. Perseverance, which landed in 2021, represents the latest chapter. It's based on Curiosity's design, but carries different instruments focused specifically on astrobiology and sample collection. Perseverance is actively collecting rock cores and sealing them in titanium tubes, creating a cache of samples that a future mission is intended to retrieve and bring back to Earth. This sample return concept has been in planning for decades, delayed repeatedly by technical challenges and funding constraints, but it remains the ultimate goal to hold Martian rocks in laboratories on Earth and study them with every analytical tool we have. Perseverance has also deployed Ingenuity, a small helicopter drone that became the first aircraft to achieve powered flight on another planet. Ingenuity was a technology demonstration intended to fly 5 times. It flew 72 times before sustaining rotor damage during landing in January 2024, ending its mission but far exceeding its design life. Once again, Mars missions seem to carry within them a capacity to surpass expectations. The Beagle 2, lander part of the European Space Agency's Mars Express mission, represents a different kind of loss. It successfully landed on Mars on December 25th, 2003, Christmas Day, but failed to establish communication. For over a decade, its fate was unknown. In 2015, high-resolution images from Mars Reconnaissance Orbiter found Beagle 2 on the surface intact, but with its solar panels only partially deployed. 2 or 3 of the 4 panels had opened, but not all, and the radio antenna remained blocked. The lander was functional, but unable to communicate stranded alone on a planet that couldn't hear it calling. It's a particular kind of tragedy success, so close foiled by a mechanical failure in the final step. Beagle 2's lead scientist Colin Pillinger had spent years developing the mission. He died in 2014, never knowing that his lander had successfully reached Mars. A year later, the images revealed it, sitting there silent but intact, a monument to how close we can come without quite succeeding. These stories aren't digressions. They're the heart of Mars exploration. Yes, the science is important, the water, the chemistry, the search for life. But the science happens because people care enough to try, fail, learn, and try again. Because engineers spend years designing spacecraft, knowing there's a significant chance it'll fail. Because scientists analyze data from missions that ended decades ago, still finding new insights. Because mission controllers sit in rooms at 2 a.m., waiting for a signal from a rover millions of miles away, hoping it woke up, hoping the commands were received, hoping the next image will show something new. Mars has taught us patience. Missions take years to plan, years to build, months to travel, and then operate on Martian time sols instead of days, with each sol 40 minutes longer than an Earth day. Mission teams have to adjust their sleep schedules to stay synchronized with rovers working on Martian time that slowly drifts out of sync with Earth time. For the first months of a mission, engineers essentially live on Mars time. Their circadian rhythms disrupted their families, adjusting all to stay connected to a machine on another world. It's a form of dedication that goes beyond professionalism into something closer to devotion. The mistakes we've made at Mars, the unit conversion error, the sensor glitch, the failed communications are now part of the institutional memory. They are taught in engineering courses, discussed in mission planning, remembered as cautionary tales. But they're also humanizing. They remind us that space exploration isn't done by infallible machines or perfect systems. It's done by people, and people make mistakes. What matters is learning from them, not being paralyzed by them. Every mission to Mars stands on the foundation of previous missions, successful and failed alike. Every rover carries within its design the lessons learned from every previous rover. We build on what came before, incrementally, patiently. There's a photograph taken by Curiosity in 2013 that shows Earth in the Martian sky about 80 minutes after sunset. Earth appears as a bright star, and if you look closely at the enhanced image, you can see the moon as a fainter point of light beside it. Every human who has ever lived, every city, every mountain, every ocean exists on that point of light. From Mars, Earth is just another wandering star. It's humbling. It makes you feel small and connected, simultaneously small, because of the vast distances connected, because we're all on that same tiny point. And somewhere on Mars, our rovers are looking back, carrying cameras built by human hands, operated by human minds, seeing what we would see if we could stand there ourselves. But looking back isn't enough. The question that pulls us forward is whether we should not just visit Mars, but change it. Whether we have the right or the responsibility to transform a planet that's been cold and quiet for billions of years into something warmer, wetter, maybe even green. Terraforming Mars isn't just an engineering challenge. It's an ethical question, a philosophical puzzle, a test of what we believe we owe to places that aren't home but might become home. And that question, with all its complexity and consequence, is where we're headed next. Imagine looking at Mars 100 years from now and seeing clouds, thick white clouds, drifting across a sky that's no longer dust pink, but deepening toward blue. Imagine rivers cutting fresh paths through ancient valleys, and at the poles, ice melting into seasonal lakes. Imagine forests, or at least the beginning of them, green spreading across red. It sounds like science fiction, and maybe it is. But it's science fiction that scientists take seriously, that engineers calculate possibilities for, that philosophers worry about. Terraforming Mars, transforming it into an Earth-like world, sits at the intersection of what we could do, what we might do, and what we should do. And those three questions don't always have the same answer. The word terraform comes from Latin terra, meaning earth, and form, meaning to shape. To terraform is to make Earth-like, to take a planet that's hostile to life, and reshape it into a place where life, specifically human life, can exist without technological support. It's planetary engineering on a scale never attempted, a project that would span centuries and cost resources we can barely imagine. But the basic physics are understood, and the theoretical pathways exist. The question isn't really whether terraforming Mars is possible in principle. It's whether it's practical, whether it's ethical, and whether we have the wisdom to do it without causing harm we can't foresee. Carl Sagan, in his 1973 paper, Planetary Engineering on Mars, was one of the first scientists to seriously propose terraforming methods. His idea was elegant place dark material on Mars's polar ice caps to absorb more sunlight, warming the poles, and causing carbon dioxide ice to sublimate into the atmosphere. A thicker atmosphere would create a greenhouse effect, trapping more heat, which would cause more ice to melt, releasing more gas, creating a positive feedback loop. It's the same process that drives climate change on Earth, but deliberately induced and controlled on Mars. Sagan estimated that even small changes in albedo, how much light the surface reflects, could trigger significant warming over decades or centuries. It was speculative, but it was grounded in real physics, and it opened a conversation that's continued ever since. The challenge is that Mars is missing most of its atmosphere. It's not just thin, it's almost gone. The planet once had a thick atmosphere billions of years ago, but after losing its magnetic field, the solar wind stripped most of it away over geological time. To terraform Mars, we'd need to replace that atmosphere, and the most accessible source is frozen carbon dioxide at the poles and possibly absorbed into the regolith, the Martian soil. Some estimates suggest Mars has enough carbon dioxide locked in its polar caps and surface to create an atmosphere with about 7% of Earth's pressure if it were all released. That's better than the current 0.6%, but it's still nowhere near Earth's sea level pressure. You couldn't breathe it, it would still be almost pure CO2, but it would be thick enough to allow liquid water to exist on the surface without immediately boiling away. That's the first step. Elon Musk has proposed a more dramatic approach: nuclear detonations at Mars's poles. The idea is that nuclear explosions would vaporize vast amounts of ice, rapidly releasing trapped gases and jump-starting the warming process. It sounds extreme, and it is, but the physics are sound. The bombs wouldn't make Mars radioactive in any meaningful way. The radiation would disperse quickly in the thin atmosphere, and most would be absorbed by the soil. What matters is the energy released the heat that would sublimate ice into gas. Musk has discussed this idea multiple times, usually half seriously, and scientists have responded with a mix of interest and skepticism. Yes, it could work theoretically, but it's also irreversible, potentially dangerous, and assumes we understand Martian ice reserves well enough to predict outcomes. We might not. And there's something deeply unsettling about solving a planetary problem by detonating nuclear weapons, even for peaceful purposes. A more gradual approach involves using factories to produce greenhouse gases, not carbon dioxide, which Mars already has, but stronger greenhouse gases like perfluorocarbons or sulfur hexafluoride compounds that trap heat far more efficiently than CO2. These super greenhouse gases could be manufactured on Mars using local materials, then released into the atmosphere, where they'd persist for centuries, slowly warming the planet. It's essentially controlled pollution, deliberately adding to Mars's atmosphere, the kinds of gases we're trying to remove from Earth's. The irony isn't lost on anyone. We'd be applying climate engineering to Mars in reverse creating global warming on purpose instead of fighting it. But here's the problem with all these approaches: even if we thicken Mars's atmosphere and warm it enough for liquid water, Mars still lacks a magnetic field. Without that protective shield, the solar wind will continue stripping away any atmosphere we create. It would happen slowly over millions of years, but it would happen. We'd be building an atmosphere on a planet that can't keep it. Some scientists have proposed generating an artificial magnetic field, perhaps by placing a massive electromagnet at Mars's L1 Lagrange point, the gravitationally stable spot between Mars and the Sun. This magnetic shield would deflect the solar wind, protecting the atmosphere below. The concept has been studied by NASA and found to be theoretically feasible, though the energy requirements and engineering challenges are enormous. We're talking about a structure that would need to generate a magnetic field strong enough to envelop an entire planet. It's the kind of project that makes terraforming Mars look like landscaping in comparison. Let's talk about timescales, because they matter. Even the most optimistic terraforming scenarios suggest it would take 100 to 200 years just to thicken the atmosphere enough for liquid water to be stable on the surface. Making the atmosphere breathable, actually adding oxygen, would take far longer, possibly thousands of years. You can't just release oxygen into the atmosphere. It's too reactive and would quickly bond with iron and other minerals in the soil. Mars's surface is one giant sponge for oxygen, having spent billions of years rusting. You'd need life to produce oxygen continuously faster than the planet can absorb it, creating a balance that slowly shifts the atmosphere towards something breathable. On Earth, it took cyanobacteria over 1 billion years to oxygenate the atmosphere. We'd need to compress that timeline dramatically, possibly by engineering super-efficient photosynthetic organisms or deploying massive arrays of artificial photosynthesis machines. Either way, it's a project measured in centuries at minimum. Which brings us to the ethics, and this is where the conversation becomes uncomfortable. If Mars is lifeless, if it's just rock and ice with interesting chemistry, but no biology, then terraforming might be acceptable. We'd be bringing life to a dead world, spreading the biosphere to a second planet, creating a backup for Earth's life in case catastrophe strikes here. That's the optimistic view, terraforming as an act of creation, of expansion, of securing life's future beyond one fragile world. But what if Mars isn't lifeless? What if there are microbes living in subsurface aquifers or frozen in the regolith, dormant but still technically alive? What right do we have to alter their environment so drastically that they couldn't survive? Would we be committing genocide against organisms we've never even discovered? This is called the planetary protection problem, and it keeps ethicists and scientists up at night. International space law, specifically the Outer Space Treaty of 1967, requires that we avoid harmful contamination of celestial bodies. If we terraform Mars without first determining whether indigenous life exists, we could be violating that principle in the most extreme way possible. We'd be destroying potential Martian ecosystems before we even knew they were there. And unlike mistakes on Earth, where species can sometimes recover or ecosystems can be restored, terraforming Mars would be irreversible on human timescales. Once you've thickened the atmosphere, warmed the planet, and introduced Earth life, there's no going back. Mars as it exists now would be gone forever. There's a parallel here to Earth's history of colonization, and it's not a comfortable one. When Europeans colonized the Americas, Africa, Australia, they often viewed these lands as empty or underdeveloped places that needed to be improved or civilized. They ignored or destroyed indigenous cultures, ecosystems, and ways of life in the process. The environmental and human costs of that colonization are still being reckoned with centuries later. Are we about to make the same mistake on a planetary scale? Mars doesn't have indigenous people, as far as we know, but it might have indigenous life. And even if it doesn't, there's an argument that Mars has intrinsic value, as it is that a cold red desert planet is no less worthy of preservation than a green Earth-like one. Do we have the right to decide that Mars should be more like Earth? Who gave us that authority? Some scientists argue for planetary parks, regions of Mars that would be permanently protected from terraforming, preserved in their natural state for scientific study, and as a matter of principle. Like national parks on Earth, these would be areas where human activity is strictly limited, where Mars can remain Mars. It's a compromise position: terraform some of the planet for human use, but leave portions untouched. The problem is enforcement. Once humanity has the capability to terraform, once there are economic and survival pressures pushing for expansion, will protected areas remain protected? History suggests that conservation often loses to development when resources are scarce and stakes are high. There's also the question of who decides. If terraforming Mars becomes possible, who has the authority to approve or reject such a project? The United Nations, individual, spacefaring nations, private companies like SpaceX, the people living on Mars, if there are permanent settlements by then. This is governance at a planetary scale, and we have no precedent for it. Earth's environmental decisions are already complicated by conflicting national interests, corporate lobbying, and short-term thinking. Imagine those same dynamics applied to a planet where different groups might have radically different visions for the future. Some might want Mars to remain pristine for science. Others might see it as humanity's insurance policy and want aggressive terraforming. Others still might want to exploit its resources without worrying about long-term habitability. These conflicts aren't hypothetical, they're inevitable if Mars development continues. Kim Stanley Robinson's Mars trilogy novels explore these tensions in fictional form, depicting a future Mars, where different factions fight over the planet's future, some wanting rapid terraforming, others advocating for preservation, others seeking middle paths. While it's fiction, it's informed fiction based on real science and real ethical debates. The novels raise questions that we need to answer in reality. What does it mean to be responsible stewards of a planet that isn't ours but might become ours? How do we balance scientific preservation with human survival needs? Can we avoid repeating on Mars the environmental mistakes we've made on Earth? Here's a perspective that often gets overlooked. Maybe the question isn't whether we should terraform Mars, but whether we should terraform ourselves instead. Rather than changing Mars to suit human biology, we could change human biology to suit Mars. Genetic engineering could potentially allow humans to thrive in lower gravity, tolerate higher radiation, or even breathe different atmospheric compositions. We could become Martian rather than making Mars become Earth-like. It sounds radical, and it raises its own ethical concerns about what it means to be human, but it's technically more feasible than planetary engineering and wouldn't risk destroying potential Martian life. We'd be adapting to Mars rather than forcing Mars to adapt to us. It's a humbler approach, one that accepts the planet as it is rather than insisting it change. Do you think a place becomes home by arriving there or by changing it to resemble the home you left? That's the heart of the terraforming debate. Is home a set of physical conditions, breathable air, liquid, water, comfortable temperature, or is it something more? Can Mars become home while remaining Mars? Or does it need to be transformed into a new Earth before we can truly belong there? Different people will answer differently, and those differences will shape humanity's future relationship with the red planet. There's something poignant about the whole terraforming discussion. Mars was once warm and wet, more Earth-like than it is now. Terraforming would essentially be returning Mars to something closer to its ancient state, undoing the death of its atmosphere and magnetic field, restoring rivers and lakes that dried up billions of years ago. In a sense, we wouldn't be creating something new, we'd be resurrecting something lost. Is that different ethically? Does it matter that Mars once had the conditions we'd be trying to recreate? Or is the Mars that exists now? The cold desert, Mars just as legitimate as the ancient wet Mars, and equally deserving of preservation. The timescales are dizzying to consider. Mars died slowly over 1 billion years, losing its magnetic field, its atmosphere, its water. We're proposing to reverse that death in mere centuries, to compress a geological process into something approaching human timescales. It's audacious. It's possibly hubristic. But it's also deeply human, this desire to not just accept the universe as we find it, but to reshape it, to leave our mark, to say, we were here and we made a difference. That impulse has driven everything from agriculture to architecture to space exploration. It's given us civilization and environmental destruction in equal measure. Whether it will give us a second home or a second regret remains to be seen. What's certain is that these decisions will be made one way or another by someone at some point. If not by us, then by those who come after. And the choices they make will ripple forward through time, shaping not just Mars, but also what it means to be human in an age where we're no longer confined to one planet. Those future humans, whether living on a transformed Mars or a preserved one, will look back and judge the decisions we made or failed to make. They'll ask whether we were wise or reckless, whether we honored life in all its forms, or privileged our own survival above all else. And we won't be there to explain our reasoning to justify our choices. We'll only be there in the consequences of those choices, written into the landscape of a planet that might be green or it might still be red, but either way will carry our legacy. The conversation about terraforming Mars is really a conversation about us, about our values, our priorities, our vision of the future. It's about whether we see ourselves as caretakers or conquerors, whether we can learn from past mistakes, or are doomed to repeat them on a planetary scale. And as we consider these questions, as we weigh the possibilities and dangers, there's one more thing to remember about Mars, one more perspective that might help us see the choice clearly. It's the view from space, the sight of both worlds together, Earth and Mars, each one precious in its own way, each one fragile, each one deserving of our best thinking and deepest care. That view, that dual perspective, is where we drift now, toward the quiet conclusion of this long journey through Martian science and human dreams. There's a photograph taken by the Curiosity rover in 2013 that shows something no human eyes have ever witnessed directly: a Martian sunset. The sun descends toward the horizon, casting light through dust suspended in the thin atmosphere, and the sky around it glows not red or orange like Earth sunsets, but blue. A soft twilight blue fading into the familiar butterscotch haze. It's backward from what we know. Our sunsets are warm, our skies are blue. On Mars, the sky is red, and the sunsets are blue. Standing there, if you could stand there, you'd watch the sun sink smaller and dimmer than it appears from Earth, 40% smaller, because Mars orbits farther out. And you'd see your home planet as just another star in the darkening sky, indistinguishable from Venus, unless you knew exactly where to look. That perspective, seeing Earth from Mars, even through a rover's camera, changes something. It makes both worlds feel more real and more fragile simultaneously. We've traveled far tonight through ancient oceans that no longer flow and polar ice that remembers when Mars breathed thicker air. We've examined rocks that hold whispers of chemistry that might once have been life. And we've considered the extremophiles of Earth that show us how life bends rather than breaks under pressure. We've traced the hidden water still locked beneath the surface, and we've understood the harsh chemistry. The perchlorates, the radiation, the cold that makes Mars so challenging and yet not impossible. We've honored the missions that succeeded and failed the humans who sent pieces of themselves across space in metal and code. And we've wrestled with the question of whether Mars should remain as it is or become something new, something green, something home. Every part of this journey circles back to the same quiet truth. We're drawn to Mars, not because it's easy or because it promises answers, but because it asks questions we need to hear. The search for life on Mars isn't really about Mars alone. It's about understanding whether life is common or rare, whether Earth is typical or exceptional, whether the universe is filled with worlds where chemistry became biology, or whether we're somehow special alone in ways we can barely comprehend. If we find even fossil evidence of ancient Martian microbes, it means life emerged independently, at least twice in one solar system. And if it happened twice here, it's probably happened countless times across billions of galaxies. That's a universe teeming with life, perhaps mostly microbial, perhaps occasionally complex, but alive nonetheless. The loneliness that sometimes settles over us when we contemplate the cosmic distances might lift just a little, replaced by the knowledge that wherever there's water and chemistry and time, there's a chance for something that breathes or divides or metabolizes something that is. But if we don't find life on Mars, if it turns out that despite having all the ingredients, water, carbon, energy, billions of years, Mars remains sterile, that's profound in a different way. It would mean that the leap from chemistry to biology is harder than we thought, that life requires not just the right conditions, but something else, some spark or accident, or specific sequence of events that might be vanishingly rare. It would make Earth more precious life, more fragile, and the responsibility to preserve both more urgent. Either answer yes, Mars had life, or no, it didn't transforms our understanding. Both are worth knowing. The uncertainty, the not knowing yet, is what pulls us forward. Consider how far we've come in just a few decades. In 1960, we didn't know what Mars looked like up close. We imagined canals and possibly forests. By 1965, we knew it was cratered and cold. By 1976, we'd touched its surface and tested its soil for life, even if the results confused us. By the 2000s, we'd confirmed ancient water and found minerals that form only in wet conditions. By the 2010s, we detected organic molecules and mapped subsurface ice. By the 2020s, we're collecting samples to bring home and flying helicopters in the Martian sky. Each decade brings us closer answering old questions and revealing new ones. The pace isn't fast. Space exploration requires patience, but it's steady accumulating building towards something significant. There are people alive today who will see the first humans land on Mars. The timelines vary depending on who you ask. NASA estimates sometime in the 2030s or 2040s. SpaceX is more optimistic. Targeting the late 2020s, though, that seems ambitious. But it will happen. The technology exists or is being developed. The will is there driven by exploration science survival instinct, or simple human restlessness. When those first astronauts step onto Martian soil, they'll carry with them everything we've learned from decades of robotic exploration, all the hard-won knowledge purchased with failed missions and patient science. They'll walk where our rovers have rolled. They'll breathe recycled air inside habitats designed to protect them from a world that doesn't care whether they live or die. And they'll look up at Earth, that blue star in the Martian night, and feel what we can only imagine the weight of being among the first humans to stand on another planet. Ambassadors not just of nations, but of a species reaching beyond its cradle. Have you ever thought about what you'd want to ask Mars if you could? Not the scientific questions we have those in abundance, but the personal ones. What did it feel like when your oceans dried? Did anything notice when the last river stopped flowing? If there were microbes in those waters, did they sense the change, generation by generation, adapting to less moisture, colder temperatures, until finally the last one died or went dormant and the silence became total? Does a planet grieve? Does geology carry memory in a way that transcends just physical recording, holding some trace of what was lost? These aren't scientific questions, but they're human ones. And maybe that's the point. We bring our humanity with us wherever we explore our capacity for wonder and sorrow and hope. Mars doesn't need us to ask these questions. We need to ask them because it's how we make meaning from the data, how we transform measurements into story. The rovers we've sent are lonelier than we usually acknowledge. Spirit and Opportunity, separated by half a planet, never communicated with each other. They only spoke to Earth. Curiosity works in isolation too far from any other active mission to coordinate. Perseverance and Ingenuity work together briefly, but Ingenuity now sits silent, rotor damaged, waiting for dust to cover it, or for future explorers to find it centuries from now. These machines operate alone in landscapes that haven't heard voices in 4 billion years, if they ever heard them at all. They're explorers in the truest sense, going where no one can follow, yet seeing things no one else sees, carrying out instructions sent from a planet that's 12 light minutes away, on average too far for real-time conversation, close enough for patience to bridge the gap. There's a psychological phenomenon called the overview effect, experienced by astronauts who see Earth from space for the first time. They describe a cognitive shift, a sudden understanding of Earth's fragility, the thinness of our atmosphere, the lack of visible borders, the realization that all of humanity shares one small planet floating in darkness. Many astronauts return, change more environmentally conscious, more concerned with cooperation and less with conflict. They've seen the whole picture. When humans eventually see Earth from Mars, that overview effect might intensify. Earth won't be a globe beneath you, it'll be a star among stars, and Mars will be the globe beneath your feet. Home will be there 140 million miles away, unreachable in any emergency. And you'll understand in your bones what it means to be truly distant, truly alone, except for the handful of people you're with. That might change us too in ways we can't predict. Mars will change us just by being there, by being reachable, by transforming from mythology to destination. For thousands of years, Mars was the god of war, a red omen in the night sky. For hundreds of years, it was an object of astronomical study, a planet with moons and seasons and polar caps. For decades, it's been a target of exploration, a place we send machines to study. Soon within the lifetime of children being born now, it might be a place where humans live, where babies are born, where communities grow. Each transformation changes not just our relationship with Mars, but with ourselves. We stop being a single planet species. We become something broader, more scattered, more resilient to any single catastrophe. That's worth something, even if we never answer whether Mars had life. The act of reaching toward it, the effort of trying to understand and eventually to inhabit expands who we are. But expansion comes with responsibility. Every footprint we'll leave on Mars, every habitat we'll build, every experiment we'll conduct, needs to be done with awareness that we're guests on a world that existed for 4.6 billion years without us. Whether Mars is alive or dead, whether it has indigenous microbes or is sterile rock and ice, we owe it care. We owe it the effort of looking before we change, of studying before we exploit, of asking permission even if there's no one to grant it. This isn't sentimentality. It's recognition that planets are rare, that Mars is the only Mars we'll ever have, and that once we've transformed it, there's no undo button. The choices we make in the next century will echo for millennia. They'll define not just Mars's future, but our own character as a species capable of reaching other worlds. The night sky holds more than we can see with naked eyes. There are billions of planets out there, some certainly Earth-like, some Mars-like, some utterly alien to anything we've imagined. Mars is simply the closest, the most accessible, the one we can reach with current technology. It's training wheels for becoming an interplanetary civilization. The skills we learn landing on Mars, surviving there, understanding its environment will translate to other worlds farther out. The patience we develop studying Mars's ancient history will serve us when we eventually study exoplanets light years away. Mars is the beginning, not the destination. It's where we learn whether we can do this, whether we have the wisdom to explore responsibly, whether we can carry our better nature with us beyond Earth's gravity well. There's comfort in incompleteness, in knowing we haven't answered everything yet. The question of Martian life remains open. The decision about terraforming is unmade. The future of human presence on Mars is uncertain. That openness is where possibility lives. Every unanswered question is an invitation to keep looking, keep wondering, keep trying. And in that trying in the decades and centuries of effort ahead, we might discover not just whether Mars has life, but what life really is, what it requires, how it begins, how resilient it can be. We might learn not just about Mars, but about Earth, seeing our own planet more clearly by comparing it to its neighbor. We might learn about ourselves, confronting our capacity for both destruction and preservation, for both short-sighted greed and long-term stewardship. Tonight, Mars is somewhere in the sky, moving through its orbit as it has for billions of years. You can't see it moving, of course the motion is too slow for human perception. But it's traveling at 54,000 miles per hour, and Earth is traveling at 67,000 miles per hour. And both are orbiting a star that's itself moving through the galaxy at over 400,000 miles per hour. And the galaxy is moving through space at speeds that make even those numbers seem small. Everything is in motion. Nothing is still. Mars and Earth dance around the sun in a pattern that brings them closer every 26 months, and then sweeps them apart again, a rhythm that's played out for as long as both planets have existed. We've only recently learned to measure that rhythm, to predict it, to use it for planning missions. But the rhythm itself is ancient and different, cosmic. When you look at Mars tonight, if it's visible in your sky, you're seeing light that left that planet about 12 minutes ago, at its closest approach longer when it's farther. You're seeing the past, as you do, whenever you look at anything distant. But with Mars, it's more noticeable. That red point isn't Mars as it exists in this exact moment. It's Mars as it was. A few minutes ago, a ghost of the present delayed by the speed of light. And if there's anyone or anything on Mars capable of seeing Earth, they're seeing our world as it was 12 minutes ago, looking at the past of a planet that's already moved on. We're always slightly out of sync, Mars and Earth never quite existing in the same moment, even when we're close. But we keep reaching toward each other anyway, across the gap, sending signals and machines, and eventually people trying to close a distance that space and time conspire to maintain. Maybe that's what this is all about. Not closing the distance entirely that might be impossible, but acknowledging it and reaching anyway. Mars doesn't need us. It's been fine without us for billions of years. But we need Mars. Or at least we need what Mars represents, the possibility of elsewhere, the knowledge that home isn't limited to one world, the dream that consciousness and curiosity and life itself might spread beyond the planet where it first emerged. Mars is hope in planetary form. It's close enough to reach, but far enough to require effort. It's harsh enough to challenge us, but not so harsh as to be completely impossible. It's the next step wherever that step leads, whether toward answers about ancient life or toward the creation of new life, toward preservation or transformation, toward knowledge or toward becoming. We've spent this night together, drifting through facts and stories about the red planet, letting science blend with wonder in the quiet hours before sleep. Maybe you've learned things you didn't know. Maybe you've felt the pull of curiosity toward a world you'll never touch, but might one day see through clearer eyes. Maybe you've simply found peace in the contemplation of deep time and distant places, in the reminder that we're part of something larger, a universe of planets and possibilities of questions asked and sometimes answered of tiny beings on one small world, looking up and out and wondering what else is there. Mars is there, red and cold and patient, holding its secrets in dust and ice, waiting for us to understand it better. Or waiting for us to leave it alone, depending on what we decide. Either way, it's there. And as long as we look up and wonder, as long as we send our questions skyward and wait for answers to come back across the void, we're connected to it. Not by gravity or atmosphere or any physical bond, but by attention, by care, by the simple act of looking and seeing and wanting to know. Thank you for drifting with me through this long night of Martian science. Thank you for your curiosity. your patience, your willingness to sit with uncertainty and complexity. The universe is vast and mostly empty, but it's also full of places like Mars, places that reward close attention, places that hold stories we're only beginning to read. There will be more stories, more discoveries, more nights of quiet exploration through science and wonder. Sleep well, knowing that somewhere out there, a planet turns red beneath a thin sky, and machines we built are still working, still exploring, still sending back pieces of answers to the oldest human question: are we alone? Dream gently. And when you wake, perhaps you'll look at the sky a little differently, knowing what's out there waiting. Good night.